Earth's first chapter was written in fire, then almost completely erased. Before continents, before oxygen, before even a stable ocean, our planet was a glowing, wounded world struck by Theia, wrapped in steam and slowly cooling beneath a newborn moon. Yet from that chaos, tiny zircon crystals still carry whispers of water touching stone more than 4 billion years ago. Welcome to Calm Earth Science, and thank you for spending your time here. If this journey into Earth's deepest past brings you a little wonder or calm, please like the video, subscribe for more quiet science stories, and share it with someone who enjoys drifting through deep time. I'd love to know where you're watching from and what time it is in your corner of the world, so leave a comment below. Now, let us begin with the Hadean Eon, the lost beginning of Earth. Earth's oldest chapter does not begin with a landscape. It begins with an absence of landscapes, with a time so remote that almost everything that once carried its evidence has been folded down, melted, buried, or remade. The Hadean Eon occupies the first great division of Earth history, beginning with the formation of the planet about 4.54 billion years ago and ending near the threshold of 4 billion years ago. It is not an eon rich with fossils, forests, continents, or familiar oceans. It is the opening condition from which all later Earth history has to be reconstructed, a time when the planet was becoming solid enough to have a surface and yet remained active enough to erase that surface again and again. The name Hadean carries an older image of a hellish world, and in a limited way that image is useful. Heat, impact, vapour, molten rock, and unstable crust all belong to this interval. Yet the danger of the name is that it can make the entire eon sound simple, as though early Earth were only a ball of fire waiting to cool. The evidence now suggests something more layered. The Hadean was violent, but not uniformly so. It may have held magma oceans and impact storms, but it may also have allowed intervals of crust, liquid water, mineral surfaces, and chemical settings that later became important to the story of life. That mixture of destruction and possibility is what gives the first chapter its quiet weight. In geologic time, an eon is one of the largest units used to divide the planet's past. Beneath eons are eras, periods, epochs, and ages, each marking smaller slices of change. These divisions are attempts to organize evidence rocks that differ from older rocks, fossils that appear or vanish, climates that shift, oceans that open and close, and chemical signatures that show a planet slowly changing its state. For the more recent parts of Earth history, the divisions can become narrow because the record is richer. There are layered sediments, preserved ecosystems, ash beds, magnetic reversals, shells, bones, pollen, ice, and many other traces that help geologists draw fine boundaries. Farther back, the record thins. Time becomes broader, not because less happened, but because less survived. The Hadean sits at that most difficult edge, where the story is immense and the surviving pages are few. This matters because the Hadean is not a decorative prologue to the real history of Earth. It is the foundation beneath every later chapter. The shape of the planet, the separation of metal and rock, the appearance of a core, the first atmosphere, the first surface waters, the origin of the moon, and the earliest chemistry all belong to this interval or press close against it. Later Earth would become a world of plate motion, oceans, atmosphere, weather, sediments, and life. But those later systems did not appear from nowhere. They were assembled from conditions established when Earth was still young, hot, and repeatedly disturbed. In that sense, the Hadean is less a single scene than a sequence of thresholds. The planet forms, it heats, it differentiates, meaning its dense metallic material sinks inward while lighter rock rises outward. It is struck by other bodies. It loses gases and gains gases. It glows, cools, breaks, and remelts. Each step narrows the range of what Earth can become, while still leaving enormous uncertainty about the details. The difficulty is that Earth itself is a poor archive of its own beginning. A planet with active geology does not preserve its earlier surfaces easily. Rock is weathered by air and water, buried under sediment, pulled into the mantle, reheated during mountain building, or transformed by pressure and fluids until its original meaning becomes difficult to read. The very processes that make Earth habitable also damage its oldest memory. On the Moon, ancient craters can remain visible for billions of years because there is no atmosphere, no rain, no oceans, and no plate tectonics to recycle the surface in the same way. On Earth, the record is more restless. The oldest known minerals are older than the oldest large surviving rocks, and even those minerals are fragments carried inside younger deposits. This is why the Hadean has to be studied indirectly, through clues that are small, scattered, and often ambiguous. The first eon must be inferred from meteorites, lunar rocks, planetary physics, chemical signatures, and rare crystals that endured while almost everything around them disappeared. That scarcity shapes the tone of the whole subject. The Hadean is not known with the same texture as the Jurassic, the Devonian, or even the Archean that followed it. There is no living forest to reconstruct, no animal body plan to compare, no broad fossil world to populate. Instead, there are ratios of isotopes, microscopic minerals, impact models, and the logic of how planets grow from disks of dust and rock. The evidence is real, but it is not always direct. It points toward conditions rather than scenes. It gives constraints rather than complete images. A zircon crystal may indicate that liquid water interacted with crust at a certain time, but it does not reveal a coastline in the ordinary sense. A lunar sample may help estimate the violence of early impacts, but it does not show exactly how every strike changed the young Earth. A model of the giant impact that formed the Moon may explain major features of the Earth-Moon system, but it still leaves room for competing details about angle, speed, mixing, and aftermath. The Hadean therefore asks for a different kind of imagination, one that stays tied to evidence while accepting that the first chapter cannot be filled in like a modern map. The broad outline begins before Earth exists as a finished planet. The early solar system forms from a cloud of gas and dust that collapses under gravity. A young sun ignites at the centre, while surrounding material flattens into a rotating disk. Within that disk, dust grains collide, stick, grow, and gather into larger bodies. Some become planetesimals, small rocky objects that serve as building blocks. Some merge into planetary embryos. The region that will become the inner solar system is crowded, hot, and unstable. Objects do not settle immediately into the orderly spacing seen today. They cross paths, they collide, they shatter and merge. Earth emerges from this environment not as a peaceful sphere placed in an empty orbit, but as one outcome of repeated accumulation. Its beginning is not a single birth moment. It is a long assembly, written in impacts and heat. That heat has several sources. Collisions add energy. Gravity compresses the growing planet. Radioactive elements release warmth as they decay. Metal sinks toward the center, giving up gravitational energy as the interior separates into layers. This process of differentiation is one of the most important transitions in early Earth history because it begins the formation of a core, mantle, and outer rocky shell. A planet that differentiates is no longer just a mixed pile of cosmic debris. It becomes structured. Its interior can store heat, drive motion, and influence the surface for billions of years. The Hadean therefore contains the start of Earth as an engine. not merely Earth as an object. Beneath any early crust, the interior is already preparing the long patterns of convection, volcanism, magnetic behavior, and chemical exchange that will shape the later planet. Yet even this structured planet remains unstable. Early Earth is bombarded by leftover material from planetary formation. It may experience global melting events. Its surface may alternate between newly solidified crust and renewed destruction. Volcanic gases collect above it. Water vapor enters the atmosphere through outgassing or arrives with water-bearing materials, and under the right pressure and temperature it may begin to condense. The Moon forms from a colossal impact, if the leading explanation is correct, and that event changes not only the sky but Earth's rotation, tides, and thermal state. These are not minor details around the edges of the story. They are part of the framework that determines what kind of planet Earth becomes. A different impact history, a different moon, a different volatile supply, or a different cooling path might have produced a world that never followed the same road towards stable oceans and enduring crust. The first section of this history must therefore move slowly around a paradox. The Hadean is the least visible eon, but it contains some of the most consequential events. It is hidden not because it was empty, but because it was active. The rocks that might have told the story most clearly were also the rocks most likely to be destroyed by the planet's own heat and motion. What remains is enough to show that Earth was never simply waiting in silence for life to begin. It was assembling the conditions under which later possibility could exist. The evidence is incomplete, and it will stay incomplete in important ways. But even through that incompleteness, the Hadean has a shape. It is the passage from cosmic material to planetary identity, from scattered dust to a world with a core, a surface, a sky, a companion moon, and perhaps, earlier than once expected, places where water touch stone. Before there are continents, before there are cells, before there is oxygen in the air or blue ocean under a familiar sky, there is this first interval of formation and erasure. The rest of Earth history begins there, not with a finished world, but with a world still learning how to become one. The material that becomes Earth begins before there is an Earth to receive it, in a cold molecular cloud drifting through the Milky Way as a wide mixture of hydrogen, helium, dust, ice, and heavier elements made in older generations of stars. Nothing in that cloud resembles a planet. It is thin by ordinary standards, spread across space in a way that would seem almost empty at human scale. Yet gravity works patiently in such places, because even a faint imbalance can become important over time. Somewhere within this cloud, a region grows slightly denser than its surroundings. It may have been disturbed by the pressure of nearby star formation, by the shock of a dying star, or simply by the slow internal motion of the cloud itself. Whatever the trigger, the result is a collapse. Material begins to fall inward. The inward fall does not produce a quiet sphere. It produces rotation, flattening, heating, and separation, because a cloud in space is never perfectly still as it contracts. Even a slight spin becomes stronger, and the forming system begins to organize itself around a center that will eventually become the Sun. This is the first setting of Earth history. Not a surface underfoot, but a disk of raw planetary possibility, with heat at the middle and dust moving in broad rings around it. The young Sun forms where the collapse is most intense. Gas piles into the center until pressure and temperature climb high enough for nuclear fusion to begin. The process by which hydrogen nuclei combine and release energy. Around that forming star, the remaining material does not simply fall in all at once. Much of it spreads into a protoplanetary disk, a rotating sheet of gas and solid particles. In this disk, distance from the Sun matters. Close to the center, temperatures are high, and only materials that can endure heat remain solid. Metals and rocky minerals survive there, while many ices are driven outward or remain as vapor. Farther from the sun, colder regions allow water ice, methane ice, ammonia ice, and other volatile materials to persist more easily. This early sorting helps explain why the inner planets become small, dense, and rocky, while the outer planets grow richer in gas and ice. Earth's future location lies inside the hotter inner disk, where rock and metal dominate the solid material. Its ingredients are not yet a planet, but they are already being filtered by temperature, gravity, and chemistry. The path from dust to planet is not a smooth enlargement in the simple sense. Tiny grains collide and stick through static forces and surface chemistry, forming slightly larger aggregates. Those aggregates collide again, sometimes joining, sometimes breaking. As size increases, gravity becomes more important. Pebbles become larger clumps. Clumps become planetesimals, bodies large enough to pull smaller material toward themselves. Planetesimals strike one another, merge, fragment, and scatter. In the crowded inner solar system, growth is both constructive and destructive. Every larger body represents many successful collisions and many failed ones. This matters because Earth's earliest nature is inherited from violence at small and large scales. The planet is not carved from one original piece. It is assembled from countless pieces, each with its own history of heating, cooling, and chemical composition. The final Earth will carry that mixed inheritance inside it. Even after melting and separation blur many of the original differences, at first, the disk may have looked orderly from a great distance, a bright young star surrounded by a flattened haze, but within it, motion is complex. Gas drags on small particles. Larger bodies disturb one another's paths. Gravity gathers material into temporary clusters, then breaks them apart when encounters become too strong. Some objects are thrown inward toward the sun. Others are scattered outward. Some collide at gentle enough speeds to add mass. Others hit with enough energy to melt or vaporize rock. The growing planets are therefore not isolated projects. They form through a shared environment of competition and exchange. The material that becomes Earth may have crossed paths with bodies that later became part of Venus, Mars, or the asteroid belt. The early solar system is a place of overlapping destinies before it becomes a set of neatly separated worlds. That older disorder is still faintly visible in the chemistry of meteorites, which preserve fragments from bodies that never became planets or were broken apart before they could fully grow. Meteorites are important because they carry some of the oldest datable material in the solar system. Certain inclusions inside primitive meteorites formed very early, before planets were complete, and they help set the age of the system as a whole. These ancient pieces show that the raw material of Earth was part of a much larger chemical story. Calcium, aluminum, iron, magnesium, silicon, oxygen, and other elements were already present in the disk, not because the solar system created them, but because earlier stars had lived and died before the sun was born. In that sense, the Hadean begins with inheritance. Earth is new as a planet, but its atoms are not new. They come from stellar processes far older than the world they will later compose. This gives the first chapter a quiet double scale, a planet forming in a few tens of millions of years from material prepared across cosmic time. The inner disk does not supply all materials equally. Water and other volatiles, which evaporate easily, are harder to retain near the young sun. This is one reason Earth's water has remained a subject of careful study. Some of it may have been incorporated during accretion in minerals and hydrated material. Some may have arrived later through impacts from water-bearing asteroids or similar bodies. Comets may have contributed in some amount, though their chemistry does not always match Earth's water as closely as once hoped. The exact balance remains debated, but the setting of the protoplanetary disk makes the question unavoidable. A rocky planet forming in the warm inner solar system has to either keep enough volatile material through its violent growth or receive enough afterward to build oceans and atmosphere. Long before the first drop of liquid water can gather on cooling crust, the disk has already shaped the limits of that possibility. As material continues to collide, the growing Earth passes through stages rather than appearing all at once. It begins as many bodies sharing nearby orbits, then becomes one of the larger planetary embryos in its region. Its gravity strengthens, its collisions become more energetic, each impact adds mass but also heat. The energy of motion is converted into thermal energy when bodies strike. Rock can melt, metal can separate, vapor can rise and escape or later condense. The early planet is built by impacts that are also furnaces. This creates one of the central patterns of the Hadean formation, and heating are the same process. To become larger is also to become hotter. To gather material is also to destabilize the surface. Accretion does not make a calm solid globe first and then warm it from within. It produces a world whose first physical state is deeply tied to the violence of its construction. The sun itself is changing during this time. Young stars are active, with stronger winds, stronger magnetic behavior, and intense radiation compared with their later calmer stages. The solar wind, a stream of charged particles flowing outward from the sun, interacts with the gas and dust remaining in the disk. Over time, this activity helps clear away leftover gas, limiting the window during which planets can gather certain materials. The inner rocky planets do not become gas giants partly because they are small, close to the sun, and formed in a region where light gases are difficult to hold. Earth will eventually have an atmosphere, but not because it captures and keeps a vast envelope like Jupiter. Its later air comes from a more fragile combination of outgassing, impact delivery, chemical reactions, and loss to space. The difference is established early. Earth forms as a rocky world with enough gravity to retain some gases over time, but not enough to remain wrapped in the deep primordial hydrogen and helium that dominate the largest planets. In the protoplanetary disk, the architecture of the solar system is still unsettled. The orbits of the growing bodies shift as they exchange energy and angular momentum. Angular momentum is the measure of rotational motion, and it controls much of the disk's behavior. Material cannot simply fall straight into the sun because its motion carries it around the center. Instead, particles spiral, collide, drift, and collect. This slow rearrangement determines where matter accumulates and where gaps open. It also controls the timing of growth. Some bodies form quickly enough to influence everything around them. Others remain small and are later swept up, shattered, or left behind. Earth's assembly depends not only on the amount of material nearby, but also on the timing of encounters and the gravitational presence of larger neighbours. A small difference in early motion could have altered which impact occurred, how much mass Earth gained, and what chemistry it retained. By the time the main body of Earth is taking shape, the solar birth cloud has already transformed beyond recognition. The original diffuse cloud has become a young star, a thinning disk, forming planets, leftover debris, and countless smaller bodies whose paths will continue to matter. Some of that debris will strike Earth in its youth. Some will become meteorites that fall billions of years later, carrying records of the time when planets were still unfinished. The Hadean is therefore not just an Earth story. It is a solar system story focused through one planet. The earliest Earth cannot be understood apart from the disk that sorted its materials, the sun that heated and cleared its neighborhood, and the collisions that gave it mass. Before core, crust, atmosphere, or ocean can be considered, There is this wider beginning dust becoming organized by gravity, heat, and motion, until one region of the inner disk gathers enough material to become the world whose later history will carry continents, seas, and life. At this stage, Earth is not yet stable, not yet cool, and not yet familiar. It is a growing concentration of rock and metal, still surrounded by danger, still unfinished in shape and chemistry. The next change is not gentle enlargement alone, but the deep transformation of that gathered material into a layered planet with an interior, a surface, and a heat that will take billions of years to fade. Accretion turns the growing Earth from a crowded swarm into a single dominant body, but the word can make the process sound too clean. It is not a quiet piling up of dust into a round stone. It is a sequence of collisions in which small bodies strike larger ones. Larger bodies absorb rivals, and every impact carries both material and heat into the unfinished planet. By this stage, the young Earth is no longer merely one object among countless grains in the inner disk. It has become massive enough for gravity to make it dangerous. Nearby fragments no longer drift past without consequence. They are bent inward, pulled into crossing paths, or thrown into new orbits by close encounters. Some arrive gently enough to add their mass without destroying the surface. Others come in with force sufficient to melt rock over enormous areas. Each collision changes the planet and changes the neighborhood around it, because as Earth grows, it clears more of its orbit and becomes better at gathering what remains. The first Earth therefore forms by removing the disorder around it, not by escaping that disorder. Its identity is built from the same impacts that make its early surface unstable. The heat created by this growth becomes one of the defining facts of the Hadean. A moving body carries energy, and when that body strikes Earth, much of that energy becomes heat. The larger the impact, the deeper and wider the melting can be. Added to this is the warmth released by radioactive elements inside the early planet. Some of these elements decay quickly by geologic standards, releasing heat during the earlier stages of formation. Gravity also adds its own contribution. As Earth grows heavier, pressure increases inside it, and as dense metal begins to sink through lighter silicate rock, gravitational energy is converted into still more heat. The result is a young planet that is not simply hot at the surface, but hot through the interior. It may pass through one or more magma ocean stages, when broad regions or perhaps nearly the whole outer planet are molten. In such a world, rock behaves less like a fixed crust and more like a deep, moving fluid that can separate, overturn, and exchange material with vapor above it. Differentiation begins when materials of different density stop remaining mixed. Iron and nickel, being dense, are drawn downward. Silicate minerals, richer in oxygen, silicon, magnesium, and aluminum, remain higher. The distinction seems simple, but its consequence is immense. Before differentiation, Earth is closer to a mixed accumulation of planetary debris. After differentiation begins, it becomes layered. A metallic core starts forming in the center, while the mantle takes shape above it. The surface, whatever fragile crust it may carry at moments, belongs to the lightest outer part of this layered system. This separation changes how the whole planet will behave. A metallic core can store and move heat differently from the mantle. It can help create conditions for a magnetic field later in Earth history, depending on its motion and cooling. A silicate mantle can convect, meaning hot material rises and cooler material sinks over very long times, carrying heat outward and feeding volcanic activity. The first Earth is becoming an engine with parts, not merely a hot stone cooling in space. This sinking of metal may have been turbulent and uneven. In a partly molten planet, blobs and streams of iron-rich liquid could descend through silicate material, gathering into larger pathways as they moved. In some models, major impacts create pools of molten metal that plunge inward, carrying heat and chemical signatures with them. The early core does not have to form all at once in a single smooth motion. It may grow through repeated additions as Earth keeps accreting and as each new impact delivers more metal to be sorted. The mantle, meanwhile, is left depleted in some elements and enriched in others depending on how strongly they prefer metal, silicate, or vapor. This is why the chemistry of rocks and meteorites matters so much to the Hadean. Elements do not simply tell what Earth contains, they tell how Earth separated itself. Their proportions become clues to the timing of core formation, the degree of melting, and the amount of material added after the main core had already formed. Earth's composition is not only the result of what it first gathered, but also of what arrived late. After much of the core separates, some impacts may still add a meaningful amount of material to the outer planet. This late veneer can help explain why certain elements that prefer metal are still present in the mantle instead of having all disappeared into the core. It is not a coating in the ordinary visual sense, but a chemical addition spread through the outer Earth by later mixing. The idea matters because core formation, mantle chemistry, volatile delivery, and impact history overlap. The planet keeps receiving new ingredients even after its internal structure has begun to settle. During this time, the surface is difficult to picture because it may not remain in one state for long. A newly formed crust can appear where molten rock cools at the top, only to be broken, buried, or remelted by the next large impact or by heat rising from below. The crust is not yet a stable platform in the later sense. It is more like a changing skin over a restless interior. In some places, it may grow thick enough to separate the atmosphere from deeper molten rock. In others, it may founder, crack, or be covered by lava, basaltic crust, similar in broad chemistry to the dark volcanic rocks that form from mantle melting, may have been common. More silica-rich crust, closer to the material that later helps build continents, is harder to produce and preserve, though ancient minerals suggest that some differentiated crust may have existed surprisingly early. The Hadean surface may therefore have included both global destruction and local persistence, with pieces of crust forming in intervals between greater disturbances. This is where early Earth begins to differ from a simple image of endless fire. A planet can be extremely hot in its interior and still develop temporary surface solids. It can suffer enormous impacts and still allow quieter periods between them. It can have magma oceans during some intervals and crustal patches during others. The earlier surface is not one unchanging condition. It is a moving boundary between heat escaping from within and cold space above. Cooling happens from the outside inward, but the interior holds enormous thermal memory. When a surface layer solidifies, it can trap heat below, slowing the release. When impacts break through or melt that layer, heat escapes differently. Volcanism opens pathways. Vapor blankets the planet and influences cooling. The young Earth is therefore governed by feedbacks, in which surface, atmosphere, and interior affect one another before any modern style of geology is established. The growing mass of Earth also changes its ability to hold material. Small bodies lose gases easily, especially under strong sunlight and impact shock. A larger Earth has stronger gravity and can retain more of what is released from its interior, though early atmospheric loss remains important. Impacts can both deliver and remove volatiles. A strike by a water-bearing body can add hydrogen, carbon, nitrogen, and other ingredients, while a larger collision can blast part of an atmosphere into space. This balance is delicate. The planet is gaining mass and chemical richness, but it is also exposed to the violence that can strip away what has gathered. The first atmosphere, if present in any sustained form at this stage, is not secure. It is built, damaged, and rebuilt. The accreting Earth is still negotiating how much of its outer inventory it can keep. Beneath these changes, the planet's shape becomes more nearly spherical as gravity overcomes the irregular forms of smaller bodies. But roundness should not be mistaken for maturity. A round early Earth can still be molten, chemically unsettled, and scarred by impacts. Its surface may glow red beneath a thick, vapor-rich sky. The Moon has not yet necessarily formed in this sequence, or it may be approaching as the consequence of the most dramatic late collision still ahead. What is already clear is that Earth's growth is preparing the conditions for that event. By becoming massive, differentiated, and thermally active, the planet is becoming capable of being transformed by one last giant encounter rather than simply destroyed by it. Accretion does not finish the Earth in the modern sense. It gives the planet mass, heat, layering, and a history of collision that cannot be removed from anything that follows. The core begins because metal sinks. The mantle begins because lighter rock remains above. The first crust appears because molten surface material loses heat to space. The early atmosphere begins because gases escape from rock and arrive with impacts, even as other impacts tear gases away. Each development is incomplete, and yet each is necessary. By the end of this stage, Earth is no longer just a gathering place for debris in the inner solar system. It is a young planet with an interior organized by density and a surface shaped by fire, impact, and cooling. What remains missing is stability. The next movement of the Hadean carries this layered but restless world into a state where molten rock, vapor, and a fragile outer skin define nearly everything, and the planet's first recognizable boundary becomes the uncertain surface of a magma ocean world. The surface of the young Earth is not yet a surface in the stable sense. It is a boundary where heat is trying to escape faster than the planet can release it, a bright, unstable skin above molten silicate, and beneath a heavy sky of vaporized rock, steam, carbon dioxide, sulfur compounds, and other gases driven out by impacts and internal heat. In a magma ocean world, stone has not vanished, but it has lost the stillness that later makes stone feel permanent. Silicate minerals melt into dense liquid. Crystals form, sink, float, dissolve, and reform as temperature and pressure change. The outer planet behaves less like solid ground and more like a deep chemical sea, with currents driven by cooling from above, heating from below, and the sorting of elements by density. This is the Hadean image that most closely matches the Eon's name. But even here, the important point is not merely that Earth is hot. The important point is that heat is organizing the planet while also making it difficult for anything to endure. A magma ocean may have formed more than once. The earliest accretional heat could melt wide regions as Earth gathered mass. The sinking of iron toward the core could add enough energy to deepen that melting. Then a giant impact, especially the collision associated with the Moon's formation, could return much of the outer Earth to an even more extreme molten state. The Hadean is therefore not one cooling curve descending smoothly from fire towards stone. It is disturbed thermal history, with episodes of melting, crust formation, renewed melting, and gradual recovery. Each episode leaves the planet changed. When molten silicate begins to cool, minerals do not all crystallize at the same time. Some form earlier and may sink or collect. Others remain in the liquid until later. Elements that fit easily into early minerals are removed from the melt first, while elements that do not fit remain concentrated in the remaining liquid. This process, called fractional crystallization, can begin to separate the outer Earth chemically even before a lasting crust exists. The magma ocean is destructive to ordinary surface memory, but it is not formless. It is a setting where the first broad chemical layering of the mantle may have been sharpened, blurred, or repeated. Above the molten rock, the atmosphere is not a familiar blue shell. It may be thick, hot, and opaque, loaded with gases released from the interior and with material thrown upward by impacts. Water, if present, can exist as vapor under conditions too hot for lasting seas. Carbon dioxide may accumulate because there is not yet a mature system of weathering, sediments, and biology to draw it down. Sulfur gases and other volcanic products add to the chemical harshness. Rock vapor itself may briefly become part of the atmosphere after the largest impacts, condensing later as droplets or fine particles. Under such conditions, the line between sky and surface becomes less clean than it is today. The air can carry the ingredients of stone. The ground can radiate heat into a sky that returns much of that heat downward. Cooling is not simply a matter of warmth escaping into space. It is controlled by the thickness and composition of the atmosphere, the brightness of the molten surface, the rate of volcanic release, and the timing of impacts that keep reopening the planet. This heavy vapor envelope helps explain why early Earth could remain hostile for long intervals, while still moving toward eventual stability. A dense atmosphere rich in greenhouse gases traps heat efficiently. Greenhouse gases absorb and re-emit infrared radiation, slowing the loss of heat from the surface. On a molten world, that effect can delay the solidification of the uppermost layers. At the same time, the young sun is fainter than the modern sun, which complicates the balance. The planet receives less sunlight than it will later, but its own internal heat and its thick atmosphere can still dominate surface conditions. The Hadean is shaped by this uneven competition between cooling space, a restless interior, and an atmosphere that does not yet behave like the one known today. At moments, the surface may be too hot for liquid water. At other moments, once enough heat has escaped and pressure remains high enough, water vapor may begin to condense in lower regions, only to be threatened again by renewed heating or impact. The transition from magma ocean to solid crust is therefore not a single clean doorway. As the uppermost molten layer cools, crystals interlock and form a crustal lid. That lid may be thin at first, dark, dense, and basaltic in broad character. Made from material produced by mantle melting, it may fracture under its own cooling stress. It may founder if denser than the material below. It may be buried by new eruptions or shattered by impacts. Still, each formation of crust matters because it changes how heat moves outward. A solid lid insulates the mantle, slowing direct heat loss from the molten or partially molten interior. Cracks and volcanic openings then become focused pathways through which heat, gases, and melt can escape. This creates an early version of a surface system, not modern plate tectonics, but a physical relationship between interior and exterior. The planet begins to develop places where rock can cool, break, react with gases, and perhaps later interact with water. Even brief crust can have consequences if it survives long enough to alter chemistry. The mineral record hints that the Hadean may not have remained entirely molten for its whole duration. Ancient zircon crystals, preserved inside much younger rocks, suggest that some silica-rich crust and liquid water may have existed earlier than a simple molten Earth picture would imply. Zircon is difficult to melt and resistant to alteration, which makes it an unusually durable witness. Its chemistry can carry signs of the environment where it formed, including interactions with water and evolved crustal material. These tiny minerals do not prove that early Earth had wide continents or calm oceans in the modern sense. They do show that the Hadean cannot be reduced to uninterrupted lava. The magma ocean world may have given way, at least locally and temporarily, to cooler surfaces capable of producing minerals that outlasted nearly everything around them. That possibility changes the emotional shape of the Eon. The young Earth remains severe, but severity does not exclude complexity. One of the hardest questions is how often the surface was reset. A large enough impact can melt regional crust, vaporize shallow water, blast material into the atmosphere, and bury older surfaces beneath ejecta and lava. Many smaller impacts can churn the upper crust without fully sterilizing or remelting the entire planet. Between those events, cooling can resume, volcanic gases can escape, rain may fall if temperatures allow condensation, newly formed rocks can interact with water, carbon dioxide, and sulfur compounds. These intervals may have been short by the standards of later geology, yet chemically meaningful. The difference between a planet that is continuously molten and one that alternates between destruction and recovery is enormous. In the second case, surface environments can appear, vanish, and reappear, giving early chemistry repeated opportunities to begin processes that do not need a permanent world at first, only usable windows in time. The deep interior also continues to evolve beneath the magma ocean or its solidifying lid, as the core forms and cools, as the mantle convects, and as crystals separate from melt. The planet's density structure becomes more defined. Some early mantle layers may be compositionally distinct, with heavier or lighter residues left by magma ocean crystallization. Whether those layers persisted or were later mixed remains uncertain. But the question matters because the mantle is not just a source of lava, it is a long-term archive of heat and chemistry. If parts of the early mantle survived mixing, then the Hadean may still have faint signatures inside modern volcanic rocks, not as intact landscapes, but as chemical memories rising from depth. In this way, the magma ocean does not only erase, it may also hide its record inside the planet, beyond the reach of direct observation, but not beyond inference. The image of a molten Hadean Earth is powerful because it feels final, as though nothing delicate could matter in such a place. Yet the more careful picture is less absolute. The molten state is central, but it is part of a sequence. Heat melts the surface, cooling forms crust, impacts destroy crust, vapors gather. Minerals crystallize, gases escape, water waits as steam, then perhaps condenses, then perhaps disappears again under renewed violence. The planet is not ready for life, but it is already developing the contrasts that make later habitability possible, interior and exterior, metal and silicate, vapor and rock, molten depth and cooling boundary. The Hadean magma ocean is therefore not only a symbol of early chaos, it is a planetary workshop in which Earth's materials are sorted, its heat is redistributed, and its first fragile surfaces begin to test whether they can last. What follows from this molten beginning is not immediate calm, but a collision large enough to become part of Earth's identity, an impact that may have remade the surface, changed the length of the day, and placed a new body in the sky. The collision that most likely formed the moon begins as a problem in motion before it becomes a familiar object in the night sky. Earth is already large, hot, and partly differentiated when another planetary body enters the story, a Mars-sized world often called Theia in scientific discussion. The name belongs to a model rather than to a preserved planet, because Theia itself no longer exists as a separate body. Its evidence is indirect, held in the angular momentum of the Earth and Moon system, the chemistry of lunar rocks, the small iron core of the Moon, and the difficulty of explaining such a large companion by simpler capture or co-formation. The leading idea is the giant impact hypothesis, a glancing collision between young Earth and Theia, energetic enough to melt and vaporize immense quantities of rock, but not so direct that the two bodies simply merged without leaving debris in orbit. From that debris, the moon accretes. A wound in the young planet becomes a companion, and that companion becomes one of the most important features of Earth's later history. A planetary embryo strikes a world that is already close to its final size. Rock does not merely fracture, it melts, sprays, and vaporizes. Metal from the impactor may plunge into Earth and merge with the growing core, while silicate material from both bodies is lofted into orbit or spread as a glowing envelope around the planet. The surface, which may have been cooling before the collision, is driven back toward a molten condition. Any early crust is destroyed over vast regions. Any atmosphere is heated, stripped, thickened, or chemically remade. The event is therefore not just a way to explain the moon, it is a thermal reset for Earth, a moment when the young planet's attempt to cool is interrupted by its own formation. Yet the collision must also be precise enough to leave the system observed today. If the impact is too weak, not enough material enters orbit. If it is too direct, the impactor may merge too completely with Earth. If it is too energetic, too much material may escape. The models that explore this event are attempts to find a narrow pathway through these constraints. In many versions, Theia strikes Earth at an oblique angle, spreading a disk of silicate debris around the planet. This disk is not a ring of cold stones. It is likely hot, partly vaporized, turbulent, and rapidly evolving. Droplets and fragments collide. Vapor condenses. Material spreads outward or falls back. Soon, the debris begins gathering into a single large body. The moon forms close to Earth, far closer than it is today, bright and enormous above a planet still radiating heat. The chemistry of the moon makes the impact story both stronger and more complicated. Lunar rocks are poor in volatile elements compared with Earth's surface rocks, which fits a hot origin, in which easily evaporated materials are lost. The moon also has a relatively small iron core, suggesting that much of its mass comes from silicate mantle material rather than from the metallic centers of the colliding bodies. At the same time, some isotopic measurements show striking similarities between Earth and the moon. Isotopes are versions of the same element with different numbers of neutrons, and their ratios can act like fingerprints of planetary source material. If Theia formed elsewhere in the solar system, its isotopic character might have been expected to differ more strongly from Earth's. The similarity has led to refined versions of the impact model, including scenarios in which the impact thoroughly mixed material from both bodies, or in which Theia formed near Earth, and therefore had a similar composition from the beginning. The broad collision remains the most convincing framework, but the details remain unsettled because the evidence points to both violence and similarity at once. A disk of debris surrounds the planet, and beyond it the growing moon begins to pull itself into shape under gravity. Close to Earth, tidal forces are strong. Tides are not only movements in ocean water, they are distortions caused by gravity acting more strongly on the nearer side of a body than on the farther side. In the earliest Earth-Moon system, these forces affect rock, melt, and later water. The young moon raises tides in Earth's molten or partly solid body, and Earth raises even stronger tides in the moon. Earth's day, at first, is probably much shorter than the modern day. Over time, tidal interactions slow Earth's spin and push the moon outward. The moon is therefore not merely a passive object placed beside Earth. From its beginning, it is dynamically linked to the planet, exchanging motion and shaping the rhythm of the system. That relationship matters for the later Earth, though its Hadean form is not the gentle tide of a modern shoreline. Before wide oceans stabilize, tides act through molten rock, early crust, atmosphere, and perhaps temporary seas. Strong tides may flex the young Earth and contribute small amounts of heating. As oceans become more persistent later on, lunar tides help stir coastal zones and shallow basins, creating cycles of wetting and drying in some environments and influencing the movement of water across the planet. The Moon also helps stabilize Earth's axial tilt over long times. Axial tilt is the angle between a planet's spin axis and its orbital plane, and it helps shape seasons. Without a large moon, Earth's tilt might have varied more chaotically under gravitational influences from other planets. That stabilizing role belongs more clearly to the long later history of Earth, but its root lies in the Hadean collision. A single impact changes not just the sky, but the range of climates and rhythms available to the planet afterward. The Moon also becomes an archive of early solar system violence in a way Earth cannot. Its surface lacks Earth's active erosion, oceans, and plate recycling, so ancient craters can persist there far longer. The lunar surface is not a perfect record of Earth's Hadean, because the Moon has its own history and its samples are limited. Still, it preserves impact evidence that Earth has mostly erased. The companion born from a terrestrial catastrophe becomes one of the tools used to study terrestrial beginnings. Earth loses most of its earliest visible record, while the body formed from that violent loss keeps a colder, more durable memory of the same era. For Earth itself, the giant impact likely deepens or renews a magma ocean. The energy deposited by the collision may leave the outer planet extensively molten, with a surrounding atmosphere rich in silicate vapor and volatile gases. As the surface cools again, minerals crystallize, gases separate, and the planet begins another stage of recovery. But this recovery happens on a changed world. Earth may have gained mass from Theia, its core may have received additional metal, its rotation has been altered, its orbiting debris has become the Moon. The impact may also affect the distribution of volatile elements, removing some and helping release others from the interior. It is a catastrophe, but not one that only destroys. It reorganizes. It sets boundary conditions for everything that follows. It is not an ornamental event, added because the Moon is visible and familiar. It marks the transition from a young planet assembled by many impacts to a planet defined by one especially consequential impact. After Theia, Earth is still hot, unstable, and hostile by modern standards. Yet it is also more recognizably part of the system known today. It has a large companion. It has a changed spin. It has a path toward tides, longer days, and a sky whose brightest night object is made from the debris of its own formation. The Moon is often treated as a symbol of calm, but its origin is bound to heat, loss, and mixing. Its quiet surface begins with material thrown violently away from Earth and then gathered by gravity into a new world. The collision does not end Hadean violence. Impacts continue. Crust forms and is damaged. The atmosphere evolves under heat and escape. Water waits for conditions in which it can endure. The significance is that one event gives early Earth a companion that will remain through all later eons. From the first oceans to the first cells, from continents to forests, from animals to observers who will eventually read lunar rocks as evidence of their own planet's beginning. Theia disappears as a separate world, but the consequences of its collision do not disappear. They are held in the Moon's orbit, in Earth's rotation, in the chemistry of lunar stone, and in the continuing effort to reconstruct a moment that remade the planet, while leaving almost no direct scar on Earth itself. What follows is the slower rebuilding of the outer world after impact. As gases rise from molten rock, volatile compounds gather above the cooling surface, and Earth begins to acquire a sky that is still far from breathable, but no longer merely empty space above stone. After the Moon forming impact, Earth's outer layers do not settle beneath a gentle sky. They breathe out a sky of their own. The first lasting atmosphere is not a transparent envelope like the modern air, and it is not a stable possession gained once and kept unchanged. It rises from molten rock, from volcanic release, from impact vapor, from material delivered by smaller bodies, and from chemical exchanges at a surface still too hot and unstable to preserve a simple record. In the Hadean, atmosphere is better understood as a moving inventory of gases around a planet that is still losing heat and still being struck. Gases escape into space, rise from the interior, break apart in sunlight, dissolve into water, or react with rock. The air is not yet a background, it is part of planetary formation itself, a restless layer between the interior and space, carrying evidence of what Earth has retained, what it has lost, and what it is still becoming. The earliest atmosphere Earth may have had was probably brief and light, made largely of hydrogen and helium captured from the solar nebula, while the young sun and its disk still surrounded the inner planets. Such an atmosphere would have been difficult for a small, hot, close-in rocky planet to keep. Hydrogen and helium are light gases, and the young sun was active, sending strong radiation and charged particles through the inner solar system. Heat gives light molecules high speeds, and strong solar activity can help strip them away. Impacts can also remove gases by shock and heating. If Earth ever carried a thin primary atmosphere from the birth cloud, much of it was likely lost early. The atmosphere that matters most for the Hadean story is therefore secondary, built from gases released by the planet and added by impacts after the first nebula envelope had faded. Outgassing is the central mechanism. As the interior melts, differentiates, and convects, volatile compounds that do not fit easily into minerals can escape from magma. Volatile means easily vaporized, and on early Earth this category includes water vapor, carbon dioxide, carbon monoxide, nitrogen-bearing gases, sulfur compounds, hydrogen, and other species depending on pressure, temperature, and the chemistry of the mantle. A volcano on modern Earth gives only a small glimpse of this process. On the Hadean Earth, outgassing could occur through broad molten regions, immense eruptions, cracks in a cooling crust, and gases separating directly from magma oceans. The surface is not sealed. It leaks the interior into the sky. Each release changes the pressure and chemistry above the planet, and the atmosphere, in turn, changes how quickly the surface can cool. The result is an airless world becoming an air-heavy world without becoming a breathable one. There is no oxygen-rich atmosphere in the modern sense. Free oxygen is highly reactive and would not accumulate before biological processes later begin producing it on a global scale. Instead, the early sky may have been dominated at different times by water vapor, carbon dioxide, nitrogen, sulfur gases, and other volcanic products. It may also have contained reducing gases, which are gases more willing to donate electrons in chemical reactions, though how reducing the Hadean atmosphere was remains debated. That distinction matters because atmospheric chemistry affects prebiotic chemistry, surface temperature, and the kinds of molecules that can form or survive. A strongly reducing atmosphere encourages some organic reactions more easily. A more neutral atmosphere changes the pathways. The Hadean does not give one simple composition that can be written down as final. It gives a range of possible skies controlled by an evolving planet. Large impacts complicate the picture. An impact can bring new volatile material, especially if the striking body contains water, carbon compounds, nitrogen, or sulfur. The same impact can also remove atmosphere by blasting gases upward with enough energy to escape Earth's gravity. Smaller impacts may deliver more than they remove. Larger impacts may strip, heat, or chemically reset the atmosphere. The moon-forming collision, if energetic enough, may have removed much of any earlier atmosphere and replaced it with a hot vapor mixture released from Earth and the impact debris. Later bombardment then adds further disturbance. This is why the first atmosphere cannot be imagined as a single continuous blanket slowly thickening through time. It may have been repeatedly damaged and rebuilt. The sky over Hadean Earth is not a settled roof. It is an active exchange layer, gaining and losing mass while the surface below alternates between molten, cooling, and shattered states. Water vapor is especially important because it connects atmosphere to ocean before a true ocean can persist. Inside molten rock and minerals, hydrogen and oxygen can be carried in forms that later release as water vapor. Impacts from hydrated bodies can add more. At surface temperatures above the boiling point under given pressure, water remains in the atmosphere as steam. Under high pressure, liquid water can exist at higher temperatures than at modern sea level. So the boundary between steam world and water world depends on both heat and atmospheric weight. As Earth cools, water vapor begins to condense where conditions allow. Rain may fall onto hot crust. It may flash back into vapor. It may collect temporarily in basins, only to be boiled again by impacts or renewed volcanism. The first hydrologic cycle, if it can be called that, is not the calm circulation of clouds, rivers, and seas. It is a harsh exchange between steam, rain, hot rock, and vapor return, with the atmosphere acting as a reservoir until the surface can hold water for longer intervals. Carbon dioxide gives the young atmosphere another kind of power. It is a greenhouse gas, able to absorb heat leaving the surface and slow its escape to space. A carbon dioxide-rich atmosphere could help keep early Earth warm even under the fainter young sun. But too much greenhouse warming, especially while internal heat remains high and water vapor is abundant, can also delay surface cooling. Carbon dioxide later becomes part of a long planetary thermostat through weathering, ocean chemistry, carbonate minerals, and volcanic return. In the Hadean, that thermostat is not yet fully established. There may be crust for carbon dioxide to react with, and there may be water at times to help weather rock, but stable continents, long-lived oceans, and later biological influence are not yet in place. Carbon dioxide is present as a powerful climate agent before the systems that later regulate it have matured. Sulfur compounds add a sharper chemical character, released by volcanism and impacts. Sulfur gases can influence atmospheric opacity, acidity, and surface reactions. Some sulfur species form aerosols, tiny particles suspended in the air. Others dissolve into water, creating acidic conditions that alter minerals. Nitrogen, less reactive under many conditions, may become an important background gas, contributing pressure even when it does not dominate chemical reactions in the same dramatic way. Pressure itself matters. A thick atmosphere changes boiling points, heat transport, and the ability of liquid water to remain at the surface. It also affects impact behavior and the way gases move between surface reservoirs. The Hadean sky is therefore not only a list of ingredients, it is a physical system, heavy or thin at different moments, warming or cooling the surface depending on composition and constantly negotiating with rock below. Sunlight changes this atmosphere from above. Ultraviolet radiation from the young sun can break apart molecules in a process called photolysis. Water vapor high in the atmosphere can be split, allowing hydrogen to escape into space while oxygen reacts with surface materials rather than accumulating freely. Methane, ammonia, and other fragile molecules can also be destroyed unless they are replenished or shielded. The upper atmosphere may expand under strong solar heating, making escape easier for light gases. In this way, early Earth's atmosphere is shaped from both directions. The interior supplies gases from below, while the sun removes or alters them from above. Between the two is a planet still trying to hold on to enough volatile material to become habitable later. This early atmosphere also prepares the surface for chemistry. gases dissolve into rain and surface water. Carbon dioxide makes water more acidic, helping it react with fresh volcanic rock. Sulfur and nitrogen compounds create additional pathways. Minerals exposed on cooling crust offer surfaces where molecules can attach, concentrate, and transform. None of this means life has begun. It means the boundary between air, water, and rock is becoming chemically active. The Hadean atmosphere is hostile to modern breathing life, but it is not chemically empty. It carries the materials and energy gradients that later questions about origins must take seriously. By the time Earth's sky begins to persist between impacts, the planet has crossed another threshold. It is no longer merely rock under space. It is wrapped in gases that remember the mantle, the impactors, the sun, and the cooling surface all at once. The atmosphere still lacks oxygen. It may be dense, hot, and unstable. It may be lost in part and restored in part more than once. Yet its presence changes everything beneath it. It slows cooling, allows pressure, holds water as vapor, permits rain when temperatures fall, and creates chemical contact between the deep interior and the outer surface. The first air is not breathable, but it is consequential. It turns the young Earth into a world with weather waiting to begin, with steam waiting to become rain, and with a surface that can no longer be understood apart from the sky pressing down upon it. Water enters the Hadean story as both an ingredient and a question, because the early Earth forms in a region of the solar system where heat makes water difficult to keep, yet the later planet cannot be understood without it. The modern world carries oceans, ice, vapor, hydrated minerals, and water locked into the deep mantle. But those reservoirs are the result of a long exchange that begins under conditions far harsher than any modern shoreline. In the Hadean, water does not first appear as calm blue ocean under a clear sky. It appears as hydrogen and oxygen held inside minerals, as steam released from magma, as ice or hydrated material delivered by impacts, as vapor trapped beneath a dense atmosphere, and eventually as liquid gathering wherever temperature and pressure allow it to remain. The central problem is not only where the water came from, it is how any of it survived a planet still hot enough to melt stone and still exposed to impacts capable of boiling seas away. Earth's water may have more than one source. Some could have been incorporated during accretion, carried in minerals that formed with water bound into their structures, or in materials that were not completely dried out before joining the planet. Some could have arrived later from bodies formed farther from the sun, especially water-bearing asteroids whose chemistry resembles Earth's water more closely than many comets do. Comets may have contributed some fraction, but measurements of hydrogen isotopes show that not all cometary water matches Earth's reservoirs well. No single clue solves the delivery problem. Instead, the evidence suggests a mixed history in which Earth gained water during growth, lost some during violent heating, received more through later impacts, and stored part of it inside the planet as well as at the surface. The giant impact that formed the Moon complicates this history. A collision that melts much of the outer Earth could drive water into the atmosphere as steam, remove some volatiles into space, and bury or mix others into the mantle. If the impact happened after Earth had already gathered significant water, then that water had to survive in some form or be replaced afterward. If much of Earth's surface inventory was lost, then later delivery becomes more important. But complete loss is not inevitable. Water can dissolve in magma under pressure. It can be carried into deeper reservoirs. It can remain chemically bound in minerals. Even under violent conditions, the planet does not behave like an open bowl emptied in a single event. Its gravity, pressure, interior storage, and continuing accretion all shape the outcome. As the surface cools after major melting, water vapor becomes one of the most important gases in the atmosphere. At first, the surface may be too hot for liquid water to last. Steam rises above molten or newly solidified rock, adding to the greenhouse effect and slowing the loss of heat. Under a thick atmosphere, however, water does not behave exactly as it does under modern pressure. Higher pressure raises the boiling point, allowing liquid water to exist at temperatures that would make it boil away at present sea level. This means early condensation could begin before the planet became gentle by modern standards. When temperatures dropped far enough, rain may have fallen from a sky dense with steam and volcanic gases. It would have met hot crust, fresh lava, glassy volcanic surfaces, and impact-heated ground. Some rain may have flashed back into vapour, some may have run across rock and collected briefly in low places, some may have seeped into fractures, reacting with minerals and carrying dissolved elements back toward basins or hydrothermal systems. The first rains would not have been a mild weather pattern. They would have been part of the planet's cooling, a transfer of heat and chemistry between sky and stone. Liquid water changes rock almost immediately. Fresh volcanic crust is chemically hungry. It contains minerals that formed at high temperature and become unstable when exposed to cooler water and carbon dioxide. Water enters cracks, dissolves ions, alters basalt, and creates new minerals such as clays and hydrated silicates. These reactions matter because they begin tying the atmosphere, crust, and ocean together. Carbon dioxide can dissolve into water and make it acidic enough to attack rock more efficiently. The weathering of rock can draw some carbon into minerals or dissolve forms, although the full long-term carbon cycle is not yet operating in its later familiar way. In the Hadean, even local water rock reactions are important because they create chemical gradients. Some places become rich in dissolved metals, others concentrate silica, salts, or simple carbon compounds. Heat from below drives circulation through fractures. The question of when Earth first had enduring oceans remains difficult because the direct rock record is so sparse. The oldest surviving minerals, especially ancient zircons, provide some of the strongest hints that liquid water interacted with crust surprisingly early. Certain oxygen isotope ratios in these crystals are often interpreted as signs that their source material had been altered by water at low temperatures before being melted and crystallized into zircon. This does not require a modern ocean, and it does not prove a planet-wide sea. It does suggest that by parts of the Hadean, there may have been surface water or near surface water capable of changing rock before that material was recycled. A world once imagined as continuously molten may have cooled enough, at least intermittently, for liquid water and crust to meet. That meeting is one of the most important thresholds in Earth history. Still, survival is not the same as permanence. Even after water condenses, impacts can disturb it. A large impact into an ocean can vaporize enormous amounts of water, send steam and rock vapor into the atmosphere, and delay cooling. Smaller impacts can still create basins, fracture crust, and supply additional volatiles. The Hadean hydrosphere, the total water system of the planet, may therefore have been episodic in its surface expression. Oceans could grow, shrink, heat, acidify, or partly vaporize. Yet if impacts become less frequent and the planet continues cooling, liquid water gains longer intervals of stability. The movement is not from no water to ocean in a single step. It is from steam dominance to intermittent liquid to more persistent surface reservoirs with setbacks along the way. The places where early water gathered would have depended on the shape of a young crust that is largely lost. Low basins may have formed from impact scars, volcanic subsidence, or uneven cooling. Without modern continents, the surface may have been dominated by dark volcanic crust, broken by highlands, fractures, and lava plains. Water would flow toward the lowest available regions, but those regions might shift as crust foundered. Lava resurfaced the ground, or impacts excavated new depressions. The first oceans, if broad enough to deserve that name, may have covered a planet with little exposed land compared with later Earth, or they may have been separated into basins across a surface still repeatedly remade. Once liquid water can persist, gravity gathers it downward, and the lowest parts of the planet become chemical meeting places. There, dissolved gases, altered minerals, volcanic heat, and impact-delivered compounds can mix. Water also moves downward as well as across the surface. Fractured crust allows circulation. Hot interiors drive convection in underground fluids. In hydrothermal systems, water enters rock, is heated, reacts chemically, and returns carrying dissolved materials. Such systems are not automatically cradles of life, but they offer conditions that later origin theories take seriously: energy gradients, mineral surfaces, confined spaces, and continuous chemical renewal. The Hadean water story therefore reaches beyond the origin of oceans. It opens the possibility of environments where chemistry does not remain dilute and static. Water is a solvent, a transporter, a reactant, and a sculptor of rock. It makes the surface more active in a different way from fire. By the later Hadean, Earth may have held water in several connected reservoirs, vapor in the atmosphere, liquid at the surface, hydrated minerals and crust, and dissolved water in the mantle. The balance among those reservoirs would change with impacts, volcanism, cooling, and chemical reactions. What matters is that water becomes difficult to remove completely once it is distributed through the whole planet. A surface ocean can be boiled, an atmosphere can be stripped in part. But water held in minerals or mantle reservoirs can later return through volcanism, and impactors can add more from outside. Earth's eventual habitability may depend on this distributed resilience. Water does not need to survive every catastrophe in one visible ocean if some of it remains hidden and returns when conditions allow. The first stable seas, whenever they fully formed, were not the end of the Hadean struggle, but they changed the planet's direction. A world with liquid water at its surface can weather rock, move heat, dissolve gases, concentrate chemistry, and soften the boundary between interior and atmosphere. It can begin leaving traces in minerals that outlast the rocks around them. It can create settings where the later question of life becomes less abstract. The Hadean Earth remains unstable, but water gives that instability new consequence. Fire builds and resets the surface. Impacts open and erase basins. The atmosphere presses down as a heavy chemical sky. And in the low places, between cooling crust and rising vapor, water begins to gather, not yet as the familiar ocean of a living planet, but as the first enduring sign that the world is moving from formation toward environment. The first crust does not arrive as a permanent shell, quietly laid over the Hadean Earth like a finished skin. It appears as a fragile consequence of cooling, a surface made possible whenever molten rock loses enough heat to crystallize at the top, and endangered almost immediately by the same planet that creates it. Beneath that surface, the mantle remains hot, mobile, and capable of feeding new eruptions. Above it, a dense atmosphere traps heat and delivers rain only where temperatures permit. Around it, impacts continue to strike, breaking, melting, and burying whatever has begun to solidify. The earliest crust is therefore not the beginning of stable ground in the modern sense. It is an experiment repeated many times, a temporary boundary between an interior still releasing formation heat and an exterior slowly becoming cold enough to preserve something. The importance of this crust lies not in its durability, because very little of it survives directly, but in what it allows. Once rock can remain solid for limited intervals, water can react with it, gases can alter it, minerals can grow within it, and the first chemical memory of the planet can begin. Most of the earliest crust was probably mafic, rich in magnesium and iron compared with later continental rocks, and broadly similar to basalt formed by melting of the mantle. When a hot mantle partially melts, the liquid that rises tends to be basaltic because the minerals that melt first create a dark, dense magma. On a young Earth with high internal heat, mantle melting could have been widespread. Lava may have covered large regions, building plains of dark volcanic rock. New crust could form quickly where lava cooled against the atmosphere or beneath water, if water was present. Yet basaltic crust is not especially buoyant compared with the mantle beneath it, especially after it cools and becomes denser. It can sink, founder, or be recycled into deeper layers more easily than lighter, more silica-rich crust. This makes the survival of early basaltic surfaces unlikely over billions of years. They may have been common in the Hadean, but common things are not always the things that endure. The record favours what resists destruction, not necessarily what once covered the most ground. The making of more evolved crust is more difficult and more revealing. Silica-rich rocks, closer in broad character to the ingredients of continents, usually require additional processing. Basalt must melt again, interact with water, separate minerals, or undergo other transformations that concentrate silica and lighter elements. On modern Earth, such processes are tied strongly to plate tectonics, subduction, and long-lived crustal recycling. In the Hadean, whether anything like modern plate tectonics operated remains uncertain. The surface may instead have behaved as a stagnant lid, a crustal shell broken by impacts, mantle plumes, and foundering but not organised into the moving plates known today. Or it may have moved in some early episodic style, with pieces sinking and overturning where dense crust became unstable. The distinction matters because it changes how quickly the planet could make varied crust, how gases returned to the mantle, and how surface water interacted with deep rock. The Hadean crust is not only a surface, it is a question about the first style of Earth geology. A stagnant lid planet can still be active. Heat builds underneath the lid. Magma rises through fractures. Large volcanic provinces can flood the surface. Dense lower crust can detach and sink. Impacts can puncture the lid and create vast melt sheets. This kind of world may produce crust repeatedly without developing global plate motion. An episodic mobile lid would be more restless, with intervals when parts of the crust break and sink, followed by periods of relative stillness, a fully plate tectonic Earth. Closer to the later planet would allow steady recycling between surface and mantle. The Hadean evidence does not yet force one simple answer. The oldest surviving rocks are too few, and the oldest minerals are too indirect. What can be said is that the planet must lose heat, and crust is part of the method by which it does so. Whether through lid overturn, volcanic resurfacing, impact mixing, or early plate-like motion, the surface is being made and unmade as the interior seeks a way to cool. The weakness of the early crust also affects water. If liquid water gathers on a basaltic surface, it does not merely rest there. It seeps into fractures, reacts with hot rock, and changes mineral structures. Basalt exposed to water can form clays, serpentine minerals, and other altered products depending on temperature and chemistry. These reactions release or consume hydrogen, change acidity, and move metals through fluids in a cracked young crust. Hydrothermal circulation may become widespread wherever heat and water meet. Water descends, warms, reacts, rises, and carries dissolved material back toward the surface. This does not require modern continents. It requires solid rock, fractures, heat, and water. Even a temporary crust can become chemically important if it survives long enough for fluids to pass through it. In that sense, the first crust transforms water from a surface reservoir into a participant in planetary chemistry. It gives water something to alter and gives the atmosphere a path into stone. Impacts both damage and create crustal settings. A large impact can melt the surface, vaporize water, and erase local geology. But it can also excavate basins, expose deeper rock, create fractures, and leave behind sheets of melt that later cool into new crust. Impact basins may become places where water collects after temperatures fall. Their fractured floors can guide hydrothermal systems. Because hot rock beneath the basin drives fluid circulation, the same event that destroys older surfaces can make new chemical environments. This dual role is one reason Hadean violence cannot be understood only as interruption. It is also part of the planet's method of renewal. The cost is memory. Each new melt sheet, eruption, and impact breccia can overwrite what came before. The early crust may have held many local histories, but most were not allowed to stay readable. As the crust thickens in places, its relationship with the mantle becomes more complex. A cooler outer layer resists motion, insulating deeper heat. This can make the upper mantle hotter beneath the lid, encouraging more melting and volcanic breakthrough. If parts of the crust become too dense, especially after cooling or chemical alteration, they may sink back into the mantle. If lighter melts are produced, they may rise and form small patches of more buoyant crust. These patches might be early steps toward continental nuclei, though the word continent can be misleading for the Hadean. It suggests large, stable land masses, while the evidence points more cautiously toward local evolved crust and perhaps small proto-continental fragments. Such fragments, if they existed, would have been precious in geological terms because their lower density could help them resist recycling. They might stand above surrounding basaltic crust, interact differently with water and atmosphere, and provide varied mineral surfaces. But their survival would remain uncertain in a world still exposed to heavy bombardment and strong internal heat. The absence of abundant Hadean rocks is itself a major clue. It shows that the first crust was either not preserved, not widespread in a preservable form, or later transformed beyond recognition. Some of the oldest known rock units on Earth date from the early Archean rather than the Hadean, and even these have often been metamorphosed, meaning changed by heat, pressure, and fluids after their formation. The Hadean crust mostly has to be approached through younger rocks that contain older minerals, through geochemical traces, and through comparisons with other planetary bodies. The Moon, Mars, and asteroids preserve ancient surfaces differently, but none is a perfect substitute for Earth. Earth's water, heat, size, and internal motion make it unique. The same qualities that eventually support a living surface make the earliest crust hard to keep. This creates one of the central ironies of deep time. The more active the planet, the less easily it preserves its own beginning. Still, the crust that vanished was not meaningless. It moderated heat flow, held water in fractures, enabled weathering, and supplied minerals to early fluids. It helped separate surface environments from the deep mantle while still allowing exchange between them. It may have provided the source material from which the oldest surviving zircon crystals formed. The early crust is therefore a lost archive that can be understood partly by its effects. It was the platform that did not last, but whose temporary existence allowed other records to begin. By the later Hadean, Earth may have had a patchwork of crustal states, new basaltic surfaces, impact melt terrains, fractured basins, hydrothermally altered zones, and small regions of more evolved rock. None of these needs to resemble a modern continent or ocean floor exactly. The planet is still young, and its geological behavior may not fit neatly into categories drawn from the present. But the shift is real. A purely molten exterior cannot hold a mineral record, cannot sustain water-rock reaction at a surface, and cannot build the chemical diversity that later questions require. A crust, even a fragile one, changes that. It gives Earth a boundary where the interior meets the atmosphere and hydrosphere in a more lasting way. The next evidence of that boundary is almost impossibly small durable crystals, older than the rocks that contain them, carrying faint signs that water, crust, and cooling had already begun to leave their marks in the Hadean world. Zircon is a small mineral with an unusual kind of patience. It can grow inside molten rock, lock uranium atoms into its crystal structure, reject lead when it first forms, and then endure conditions that would destroy or transform many other minerals. That makes it one of the most valuable witnesses to the Hadean, because the rocks around the oldest zircons are not Hadean rocks in the full sense. They are younger deposits that contain older grains, tiny survivors carried from vanished crust into later sediments and then preserved through another long sequence of burial, heating, and exposure. A zircon crystal can be smaller than a grain of sand, yet it may hold information from a world almost entirely erased. It does not show a coastline, a volcano, a basin, or a sky. It gives something narrower and in some ways more powerful a date, a chemical signal, and a constraint on what conditions had to exist when it formed, in a period where landscapes are gone. Such constraints become the nearest thing to memory. The most famous Hadean zircons come from the Jack Hills region of Western Australia, where individual crystals have been dated to more than 4 billion years old, with some approaching about 4.4 billion years. The age is measured through uranium-lead dating, a method that depends on the radioactive decay of uranium isotopes into lead isotopes over known rates. Because zircon accepts uranium into its structure when it crystallizes but tends to exclude lead. Lead found later inside the crystal can be interpreted as the product of decay. If the crystal has remained sufficiently closed to later disturbance, ancient grains can be altered, cracked, reheated, or affected by later fluids. So the measurement must be careful. But when the results hold, the implication is extraordinary. A mineral formed within a few 100 million years of Earth's assembly has survived long enough to be read in the present. The planet erased its first crust everywhere, yet a few crystals escaped the erasure. Their importance is chemical as well as chronological. Some contain oxygen isotope ratios that are difficult to explain if they formed only from dry, primitive mantle melt. Oxygen isotopes are forms of oxygen with different masses, and their proportions can shift when rock interacts with liquid water at relatively low temperatures near the surface. If a zircon grows later from melted material that had previously been altered by water, the crystal can inherit that signature. This has led many researchers to argue that liquid water was present at or near Earth's surface earlier than a simple global magma ocean picture would suggest. A zircon does not prove a calm ocean spreading across the entire planet. It does not prove continents in the modern sense. It does not even preserve the exact rock body in which the water interaction first happened, but it can imply that some crust existed. The water touched that crust, and that the altered material was later recycled into magma from which zircon crystallized. That chain is delicate, yet it changes the Hadean from a blank inferno into a planet with intervals of surface chemistry. Zircon also offers clues about the kind of crust that may have existed. Many zircons form more readily in silica-rich melts than in simple basaltic melts, because zirconium becomes concentrated during the evolution of magma. This has encouraged the idea that at least some Hadean crust had become chemically differentiated, meaning it was processed beyond the first dark basaltic surface formed directly from mantle melting. The existence of a zircon does not demand large continents. It may point instead to small, local, repeatedly destroyed pockets of evolved crust, generated and recycled in a restless young world. The mineral is precise in its survival but limited in its geography. It remembers a condition, not a map. The hafnium isotopes inside some zircons add another layer. Hafnium is an element that can help trace the history of crustal extraction from the mantle. Its isotope ratios can indicate whether the magma that formed a zircon came directly from a mantle source or from older crust that had already been separated and reworked. Some Hadean zircon studies have been interpreted as evidence for very early crust formation followed by recycling. The details are debated, because different analytical methods and later disturbances can complicate the signal. Still, the larger question is clear. If the Hadean mantle had already produced crust that survived long enough to be remelted, then Earth's outer shell was not merely forming and vanishing in single events. It was developing a short-term crustal cycle with materials extracted, altered, buried, melted, and crystallized again. This is not necessarily plate tectonics as known today. It is a more cautious image. Early crust moving through processes of creation and return, leaving only mineral fragments as testimony. The durability of zircon creates a strange imbalance in the record. A mountain range can vanish, an ocean basin can be destroyed, a volcanic province can be recycled into the mantle, but a zircon, if it is carried into sediment and protected by later rocks, can persist. Its survival is partly chemical, partly physical, and partly accidental. Zircon is hard, resistant, and dense. It can withstand weathering that breaks down other minerals. Rivers can transport it. Sediments can bury it. Later metamorphism can overprint parts of its history, but sometimes the core of the crystal remains readable. When geologists examine such grains, they may find zones inside them, like growth rings at microscopic scale, each recording a different episode of crystallization or alteration. In the Hadean context, even one preserved core can matter because it reaches back into a time that almost nothing else does. Yet zircon evidence also shows why deep time demands restraint. The temptation is to turn each ancient grain into a complete scene rainfall on black rock, shallow seas under a dim young sun, islands of early crust rising from a warm ocean. Some of those images may be plausible, but the mineral alone does not supply all of them. It supplies boundaries. It says that the temperature, chemistry, and source material were not arbitrary. It narrows what can be imagined without replacing uncertainty with certainty. The best reading of zircon is therefore both bold and modest. Bold, because it allows liquid water and evolved crust to enter the Hadean earlier than older, simpler models allowed. Modest, because it does not settle the extent, duration, or stability of those environments. The evidence is not weak, but it is thin. It is a narrow beam shining through a very large darkness. The oldest zircons also raise the question of how quickly Earth recovered after the moon-forming impact. If some grains really formed about 4.4 billion years ago, then parts of the outer planet must have cooled enough for crustal processes within a relatively short interval after the major stages of formation. That does not mean the whole surface was calm. It means cooling and crust production could occur faster, or more locally, than a purely molten vision permits. Large impacts could still reset broad regions. Magma oceans could still have existed earlier or after particular collisions. But between and after such events, the surface may have crossed into solid and wet conditions repeatedly. The importance lies in rhythm. The Hadean may have been a pulsing world, moving between heat and recovery, not a single state held for hundreds of millions of years. Zircon remembers the recovery moments because those are the moments in which crystals can grow. There is another quiet consequence. If water and crust were present early, then the settings relevant to prebiotic chemistry may also have appeared early, even if life itself had not yet begun. Water-altered rock, minerals offered surfaces, heat drove fluids through fractures, impact basins and volcanic terrains created chemical contrasts. Zircon does not prove any of this directly, but it helps make such environments geologically plausible. It shows that Earth was producing surface materials that could participate in more complex chemistry. This matters because the transition from Hadean to Archean includes some of the earliest possible evidence for life or life-related processes. The timing remains difficult and debated, but a planet with early water-rock interaction is a more prepared planet than one that stayed molten and dry until the last moment. The crystal record does not announce life. It makes the stage less impossible. In the end, Zircon is powerful because it is so small compared with the question it addresses. The Hadean asks about a whole world, its heat, its water, its crust, its atmosphere, its impacts, and its first chemical pathways. Zircon answers with fragments. It gives ages older than surviving rocks. It gives oxygen signals that point toward water. It gives trace elements and isotope systems that hint at differentiated crust and recycling. It gives no complete landscape, no continuous chronology, and no final settlement of the debate. But without these crystals, the earliest Earth would be far more silent. They are not the Hadean itself. They are what remained after the Hadean passed through destruction, burial, erosion, and time. Their testimony is partial, but it is enough to change the outline of the first eon. The young Earth was not only molten, it was also, at least in places and intervals, cool enough to make crystals that remember water touching stone. That is the significance of Zircon memory, not that it removes uncertainty, but that it prevents the beginning from being imagined as emptier than it was. Bombardment gives the Hadean Earth one of its most difficult contradictions. The same impacts that help assemble the planet also erase the evidence of its assembly, and the same collisions that threaten any early surface can create new basins, new melts, new fractures, and new chemical settings. By the later Hadean, the solar system has become more organized than the original protoplanetary disk, but it is not empty. Leftover planetesimals, fragments from broken bodies, and objects scattered by changing orbits continue to cross the paths of the inner planets. Earth, large and gravitationally inviting, receives some of this material. The Moon receives it too, and because the Moon preserves ancient scars far better than Earth, its cratered highlands have often been used as a rough window into the violence that Earth itself has mostly lost. The image is not of a single rain of stones falling at one steady rate. It is a changing impact environment, intense early, declining with time, perhaps interrupted by pulses, and always capable of resetting local surfaces just when they were beginning to hold a record. A small impact into young crust may excavate a crater, melt a limited region, and throw debris outward. A larger one can create a basin many hundreds of kilometers across, fracture the surrounding crust, drive hydrothermal circulation, and bury earlier rock beneath ejecta. A still larger collision can vaporize water locally or globally, melt huge areas of crust, and fill the atmosphere with hot vapor and fine particles. The size of the impactor matters, but so do speed, angle, target rock, ocean depth if water is present, and atmospheric pressure. Hadean bombardment is therefore not one process but a spectrum of processes. Some impacts are brief disturbances, others are planetary events. Between them are countless intermediate collisions that churn the surface without necessarily destroying the whole possibility of surface environments. This difference matters because the Hadean is often imagined as either completely sterile violence or quietly cooling stability. When the likely reality lies between those extremes, impacts can be severe and still leave intervals where water, crust, and chemistry return. The concept often associated with this time is the late heavy bombardment, a proposed interval of elevated impacts near the end of the Hadean and the beginning of the Archean. The idea grew largely from studies of lunar samples and crater ages, which seemed to suggest a clustering of major impacts. Later work has complicated that picture. Some researchers interpret the evidence as a sharp spike, while others see a longer decline from earlier accretion, with sampling limits and lunar geology affecting the apparent pattern. For Earth, the distinction is important but difficult to settle. A sharp bombardment pulse would mean a dramatic late disturbance after some crust and water may already have formed. A long declining bombardment would mean that heavy impacts were simply the fading tail of planetary formation, still dangerous but not necessarily concentrated into one brief episode. Earth does not preserve enough direct surface evidence to decide the issue easily. Its record has been recycled, metamorphosed, and broken apart. The Moon keeps craters, but Earth must infer its own wounds from a companion, from impact models, and from rare geochemical hints. Even without a single settled bombardment curve, impacts clearly shape the Hadean surface. They can destroy early crust, but they can also make crustal material. When an impact melts rock, the melt can cool into a new sheet. When it excavates a basin, it exposes deeper material to surface water and atmosphere. When it fractures crust, it opens pathways for fluids. Hot impact melt beneath a basin can sustain hydrothermal systems for long intervals by human standards. Possibly thousands or millions of years depending on the size of the structure and the thermal conditions. In those systems, water circulates through hot rock, dissolves minerals, carries metals and silica, and returns altered. Such places are not calm in origin, but after the violence fades they may become chemically active environments. This is one of the more subtle meanings of renewal in the Hadean. Renewal is not gentleness. It is the creation of new surfaces and new gradients after destruction has passed. Water makes bombardment more complicated. If oceans or regional seas exist, an impact into water can produce steam, waves, ejecta, and intense mixing. A sufficiently large impact may boil an ocean at the surface or fill the atmosphere with water vapor, but the outcome depends on scale. Not every impact sterilizes the planet. A global ocean has depth, heat capacity, and circulation. The crust beneath it can absorb, conduct, and release heat. If life had not yet begun, the issue is not survival of organisms, but survival of environments. If prebiotic chemistry was underway, the question becomes whether impacts interrupted it completely or repeatedly refreshed the conditions under which it could restart. Even in severe scenarios, water stored in the mantle or hydrated minerals could later return through volcanism, and incoming bodies could deliver additional volatiles. The Hadean hydrosphere may have suffered repeated shocks, yet it was not necessarily a fragile surface film lost forever at the first catastrophe. Atmosphere responds just as strongly. Impact energy can drive atmospheric escape, especially for light gases or for upper layers accelerated beyond Earth's gravity. At the same time, vaporized impactor material and target rock can add gases and particles. Carbon dioxide, water vapor, sulfur compounds, and metal-rich aerosols may all enter the sky after major events. The atmosphere can warm, darken, acidify, or temporarily change its ability to transmit sunlight. Fine particles may block incoming light for a time, while greenhouse gases trap heat. Rock vapor can condense and fall back as droplets or dust. The air after a great impact is not simply thicker or thinner. It is chemically altered. Such changes feed back into the surface, because climate, rainfall, ocean chemistry, and weathering depend on what the atmosphere contains. A bombardment history is therefore also a climate history, though one written in violent punctuation rather than smooth cycles. The incompleteness of the terrestrial record is partly a consequence of these impacts, but impacts are only one form of erasure. Earth's internal activity continues the work. Crust that survives collision can later be buried, heated, folded, or drawn down into the mantle. Sediments can be metamorphosed until their original environment is difficult to recover. Minerals can be reset by heat or altered by fluids. This is why the Hadean remained so dependent on indirect evidence. The early surface was not merely old, it was repeatedly denied the conditions needed for preservation. To preserve a rock for billions of years, it must avoid melting, deep burial, intense deformation, chemical destruction, and recycling. In the Hadean, those hazards are not rare exceptions. They are part of the planet's normal behavior. The scarcity of rocks is therefore not surprising. The surprise is that anything survived at all. Yet the absence of a broad rock record should not be mistaken for absence of environments. A surface can exist and vanish without leaving a surviving outcrop. Oceans can interact with crust and later be erased from direct view. Hydrothermal systems can alter rock whose minerals are later scattered or destroyed. Impact basins can host chemistry and then disappear into the mantle. The geological archive is selective, and in the Hadean it is especially severe. Zircons and a few chemical signatures are not the whole story, only the pieces that pass through the filter. This gives early Earth a strange quality. It may have been more varied than the record can show, with places of molten rock, cooling crust, temporary land, shallow water, deep basins, hot springs, impact seas, and vapor-heavy skies existing in shifting combinations. Bombardment repeatedly rearranged those combinations, preventing long stability, but creating new settings with each disturbance. The decline of impacts over time becomes one of the quiet thresholds leading toward the Archean. As leftover debris is swept up, ejected, or locked into more stable reservoirs, the intervals between major collisions lengthen. Crust has more time to cool. Water has more time to persist. Atmosphere has more time to respond to internal outgassing and surface reactions rather than constant shock. Hydrothermal systems can run longer before being reset. Sediments, where they form, have a better chance of being buried and preserved. This does not mean the end of impacts, because Earth continues to be struck throughout its history. It means impacts become less dominant as a global surface-forming process. Volcanism, weathering, mantle convection, ocean chemistry, and eventually biology begin to take more of the planet's narrative weight. The Hadean bombardment is therefore not simply an age of destruction before real geology begins. It is part of real geology, only written at a scale and intensity that later Earth rarely repeats. It delivers materials, removes gases, opens basins, melts crust, drives fluids, and erases records. It forces the planet to rebuild itself more than once. By the time bombardment weakens, Earth has not escaped its violent origin, but it has passed through enough renewal to make longer-lived environments possible. The surface remains young in the sense that most older surfaces are gone, yet the planet beneath has matured. Heat is still moving outward. The core and mantle continue their slow exchange of energy. Crust forms with greater persistence. Water can remain for longer intervals. The next question is no longer only how Earth survived impacts, but how the heat inside the planet kept shaping the world after the rain of debris began to fade. Deep inside the Hadean Earth, heat is not a leftover detail. It is the main force that keeps the young planet changing after the first great collisions begin to fade. The surface may cool into crust, the atmosphere may gather above it, and water may find low basins. But beneath those outer signs, the interior remains far from quiet. Earth has inherited heat from accretion, from the sinking of metal, from radioactive decay, and from the moon forming impact. That heat cannot escape all at once. It moves slowly through a body thousands of kilometers deep, crossing materials that differ in density, melting point, and ability to flow. The planet therefore becomes an engine whose fuel is its own formation. Even when the surface begins to look less violently molten, the interior continues to stir, separate, and release energy. This inner motion is one reason the Hadean does not end simply because impacts become less common. The planet itself remains capable of remaking the surface from below. The core is the deepest expression of this early sorting. As iron-rich metal sinks through silicate rock, it gathers toward the center and forms a dense metallic region surrounded by the mantle. Much of this separation may have happened early, while the outer Earth was partly or largely molten. Because metal can move more efficiently through liquid or softened silicate than through a cold solid planet, the descent of metal releases gravitational energy and adds more heat. It also removes many metal-loving elements from the mantle, changing the chemistry of the outer Earth. The core that forms is not merely a storage place for iron and nickel. It is a reservoir of heat and motion, whose later behavior affects the entire planet. In the modern Earth, movement in the liquid outer core helps generate the magnetic field. In the Hadean, whether a strong magnetic field existed when it began, and how stable it was remain active questions. But the possibility matters because magnetism can influence how a planet interacts with the solar wind. A magnetic field does not seal a world from space completely, yet it can help shape the escape of charged particles in the upper atmosphere. Above the core, the mantle is not liquid in the ordinary sense, but over geological time it can flow. This slow movement is convection, driven by heat rising from below and cooler material sinking from above. In the Hadean mantle, higher temperatures make this process more vigorous than in later Earth. Hot mantle material rises, partially melts as pressure decreases, and feeds volcanic activity. Cooler, denser material near the surface may sink or founder, carrying altered crust downward. The style of that motion is uncertain. It may not match modern plate tectonics, where rigid plates move, collide, sink, and spread in a connected global system. The early mantle may instead have driven a hotter, more episodic form of overturn. With crustal lids breaking, dense sections sinking, and plumes of hot material punching upward, what remains clear is that heat must find pathways outward, and the mantle is the great medium through which that heat moves. The first crust is shaped by this inner motion. A solid lid slows heat loss, but it also creates pressure beneath itself. When the mantle melts, magma rises through weak zones and fractures. When dense crust forms at the surface and cools, it can become unstable and sink back into hotter material. When water alters rock near the surface, it changes density and melting behavior, so the return of that material to depth can influence the chemistry of later magmas. These exchanges may be messy and local rather than globally organized, yet they are still important. They connect surface water, atmospheric gases, and deep mantle melting into a single planetary cycle in early form. Earth is not yet operating with the full rhythms of later geology, but the pieces of those rhythms are beginning to appear. Heat moves upward, rock melts, gas escapes, crust cools, some crust returns downward. Each step changes the next. The Hadean mantle may also preserve chemical memories of the magma ocean. As a deep molten layer crystallizes, minerals form in a sequence, and some may sink while others remain suspended or rise. This can create layers with different compositions. Later convection may mix these layers, but perhaps not completely. Some modern volcanic rocks have been studied for hints of very ancient reservoirs, possible traces of material separated during the earliest history of the planet. Such interpretations are difficult, yet the possibility is important. The Hadean is not only lost at the surface, parts of it may be hidden in the deep earth, carried forward as subtle chemical differences inside the mantle. The planet may have erased its first landscapes while keeping faint internal residues of the processes that destroyed them. Radioactive decay adds another steady source of heat. Elements such as uranium, thorium, and potassium release energy as their atoms change into other forms. In the early Earth, some short-lived radioactive isotopes also contributed heat soon after formation. Over time, radioactive heat declines, but in the Hadean it helps maintain a hotter interior. This heat affects melting, volcanism, crustal production, and the cooling of the core. The rate of heat loss influences mantle convection, crustal recycling, and the motion needed for a magnetic field. The interior is therefore linked to the atmosphere and hydrosphere in indirect but profound ways. A hotter mantle releases more volcanic gases. More volcanic gases affect atmospheric pressure and climate. Climate controls the state of surface water. Water alters crust, and altered crust may later return downward, carrying new chemical effects into the interior. The question of an early magnetic field sits at the boundary between the core and the sky. Today, Earth's magnetic field is generated by a geodynamo, a process involving the motion of electrically conducting liquid metal in the outer core. For a dynamo to operate, the core must move in organized ways, driven by cooling, compositional differences, and planetary rotation. In the Hadean, Earth rotates faster than today because the Moon is much closer, and tidal interactions have not yet slowed the planet as much. Faster rotation can help organize flow, but the core also has to lose heat efficiently enough to drive motion. Some ancient minerals from later rocks have been interpreted as possible evidence of an early magnetic field, though the oldest part of this record remains debated and technically difficult. If a Hadean magnetic field existed, it may have helped reduce atmospheric loss under the active young sun. If it was weak or intermittent, the atmosphere may have been more exposed. Either way, the issue shows how deeply the interior reaches into questions of habitability. A process thousands of kilometers below the surface can influence what happens at the edge of space. Volcanism is the visible language of this internal heat. On the Hadean Earth, eruptions may have been more extensive and more frequent than in later eras, fed by a hotter mantle and thinner or less stable crust. Lava resurfaces terrain, releases gases, builds volcanic plateaus, and covers older rocks. Underwater, eruptions form glassy crust and hydrothermal systems. On land or shallow surfaces, they create fields of fresh minerals ready to react with atmosphere and rain. Volcanism is destructive when it buries earlier surfaces, but it is also renewing. It brings deep material upward, supplies carbon dioxide, water vapor, sulfur gases, and other volatiles, and creates the rock that water later alters, in a Hadean setting where preservation is poor. Volcanism may have been one of the most consistent ways for the interior to keep the surface chemically alive. It is not only the eruption that matters, but the aftermath: cooling lava, cracking rock, circulating fluids, and gases entering the atmosphere. The heat inside Earth also determines the pace of stabilization. A small planet loses heat quickly and becomes geologically quiet. A much larger one may hold heat but develop crushing pressures and different surface conditions. Earth occupies a middle path, large enough to remain active for billions of years, small enough to have a solid surface and later oceans. In the Hadean, that balance is still raw. Too much heat keeps the surface unstable. Too little heat would shut down the recycling and outgassing that helps sustain atmosphere and long-term habitability. The young planet has to cool, but not die. Its interior must release enough energy to allow a crust, water, and atmosphere to persist, while retaining enough motion to keep geochemical cycles from freezing into stillness. It is the outcome of mass, composition, impact history, radioactive inventory, and distance from the Sun. By the close of the Hadean, Earth has not become a calm planet, but its internal engine is taking a more enduring form. The core holds deep heat and perhaps begins the long path toward magnetic protection. The mantle convects, melts, and feeds crust. Volcanism carries gases and rock upward. Crust forms, breaks, and sometimes returns downward. Water, where present, reacts with this crust and becomes part of the chemical exchange between surface and depth. The planet's violence is no longer only arriving from space. Much of its power now rises from within. That shift is quiet but decisive. Impacts may continue to scar the surface, yet the deeper story increasingly belongs to Earth's own machinery. The next threshold lies where that machinery meets chemistry. In the marginal environments where hot rock, water, minerals, and gases begin creating reactions more intricate than simple cooling alone. Chemistry at the margins begins where the Hadean Earth is neither purely molten nor fully settled. In places where water touches hot rock, gases dissolve into shallow pools, minerals expose reactive surfaces, and energy moves through narrow gradients rather than through planet-wide catastrophe. A whole ocean is vast, yet vastness can dilute. A global atmosphere is powerful, yet its gases can remain spread too thin for certain reactions to proceed. A molten surface contains enormous energy, but often too much of it, destroying complex molecules as quickly as they form. The useful settings are more particular. They are cracks in cooling crust, pores within minerals, wet and dry edges around basins, hot springs, impact-heated systems, and seafloor vents where water, rock, and heat meet in confined spaces. The Hadean does not need to provide a gentle world for prebiotic chemistry to begin exploring pathways. It needs intervals and locations where ingredients can gather, react, and avoid immediate destruction long enough for new forms of organization to appear. Prebiotic chemistry means chemistry before life, but the phrase should not be treated as if there were one simple ladder from ordinary molecules to the first cell. Life, even in its simplest known form, involves linked systems, molecules that store information, structures that create boundaries, reactions that harvest energy, and a way for useful patterns to persist. The Hadean question is not how a complete living cell suddenly appears from hot water and stone. It is how non-living chemistry might begin to acquire pieces of those functions in a world still changing around it. Some pathways focus on organic molecules, compounds built around carbon. Others focus on concentration, because molecules scattered through an ocean may never meet often enough to matter. Others focus on energy, because reactions that build complexity usually require a source of drive. Still others focus on surfaces, where minerals can hold molecules in place, orient them, or help reactions occur that would be unlikely in open water. The difficulty is not the absence of possible pathways. The difficulty is making enough of them work together under conditions that early Earth plausibly offered. Hydrothermal systems are one important candidate environment because they naturally combine water, heat, minerals, and chemical gradients. Water seeps into fractured crust, is heated by hot rock or magma, reacts with minerals, and returns carrying dissolved substances. On the sea floor, this can create vents where warm or hot fluids mix with colder ocean water. Some vents are acidic and metal-rich. Others, especially alkaline hydrothermal systems, produce fluids with abundant hydrogen through reactions between water and iron-rich rock. The contrast between vent fluids and surrounding seawater can create chemical disequilibrium, a state in which reactions have usable energy because the system has not settled into balance. Modern life depends on exploiting disequilibrium. The earliest chemistry, if it occurred in such settings, may have used natural gradients before biology learned to control them. Mineral walls and tiny pores could have acted as compartments, holding reactants close together and maintaining differences across small boundaries. Another possible setting lies at the surface, where pools, shorelines, volcanic flats, and impact basins experience cycles of wetting and drying. These cycles matter because water is both helpful and difficult. It dissolves molecules and allows them to move, but it can also keep molecules too dispersed. When a shallow pool dries, dissolved compounds become concentrated. Molecules that rarely meet in dilute water may come into contact on mineral surfaces or in shrinking films. When water returns, the products can be redistributed and tested in new conditions. Repeated drying and re-wetting can encourage reactions that build longer chains from smaller units, including molecules relevant to nucleic acids or peptides in laboratory studies. The Hadean surface may have offered such cycles if exposed land or shallow volcanic islands existed, though the extent of dry land remains uncertain. A world covered entirely by deep ocean would favour different pathways from a world with scattered hot basins and intermittent shorelines. The zircon evidence for early crust and water allows surface settings to be considered, but it does not prove how common they were. Mineral surfaces provide a quieter form of organisation. Clays, metal sulfides, iron-nickel minerals, and other reactive materials can bind organic molecules, concentrate them, and sometimes catalyse reactions, meaning they help reactions proceed without being consumed. Fresh Hadean crust would have supplied abundant minerals not yet softened by long weathering. Impacts would expose deeper rock. Volcanism would lay down glass and ash. Hydrothermal fluids would precipitate new minerals as hot water mixed with cooler surroundings. Each surface has its own chemistry. Some attract certain molecules and not others. Some provide metal atoms that assist electron transfer. Some create tiny spaces where concentration and protection become possible. These details matter because origin of life chemistry is not only about ingredients in a bowl, it is about the physical setting that decides which ingredients meet, how long they remain together, and whether a reaction product survives long enough to take part in another step. Organic molecules themselves may have formed on Earth, or arrived from beyond it. Carbon chemistry occurs in space, in meteorites, and in the icy and dusty material left from planetary formation. Some meteorites contain amino acids and other organic compounds, showing that abiotic organic chemistry is not unique to Earth. Hadean impacts could therefore deliver organic material as well as water and metals. At the same time, impacts can destroy organics through heat, volcanic gases, lightning, ultraviolet radiation, hydrothermal reactions, and atmospheric chemistry may also have produced organic molecules locally, depending on the composition of the early atmosphere. A more reducing atmosphere would favour some syntheses, while a more neutral carbon dioxide and nitrogen-rich atmosphere would require different pathways or localised reducing environments. The planet may not have needed one atmosphere that made all prebiotic chemistry easy. It may have provided a patchwork of microenvironments where certain reactions were favoured in one place and other reactions somewhere else. The question of inheritance is especially difficult. Life is not merely chemistry that becomes complex. It is chemistry that can carry information forward. Modern organisms use nucleic acids to store genetic information, proteins to perform many catalytic tasks, and membranes to maintain internal environments. Which came first? or how these functions emerge together, remains unresolved. The idea of an early ribonucleic acid world proposes that molecules related to ribonucleic acid may once have both stored information and catalyzed reactions. This is attractive because it combines two roles in one molecule type, but it faces challenges, including how its building blocks formed, concentrated, linked, and survived under realistic early Earth conditions. Other hypotheses place metabolism first, suggesting that networks of energy releasing reactions on mineral surfaces may have developed before genetic molecules became central. Still others emphasize compartments, because without boundaries, useful chemical systems may disperse before they can evolve. The Hadean does not yet choose among these ideas. It provides possible settings in which each can be tested against geology. Energy is the common requirement running through all of them. Sunlight reaches the surface, though ultraviolet radiation can be both useful and destructive. Lightning may drive reactions in the atmosphere. Impacts deliver sudden heat and create long-lived hot zones afterward. Radioactive decay and mantle heat power hydrothermal circulation, redox gradients, involving the transfer of electrons between molecules, can provide chemical energy when reduced fluids meet more oxidized surroundings. Differences in acidity can also store usable energy across boundaries. Modern cells maintain such gradients with exquisite control, but in the Hadean, natural environments may have supplied primitive versions. Whether early chemistry could harness such gradients before true cells existed is uncertain, but the possibility links origin scenarios to physical Earth processes rather than to abstract mixtures of molecules. The greatest caution is that plausible settings are not the same as proven beginnings. Hydrothermal vents exist as a coherent idea, but ancient Hadean vent systems are not preserved in direct detail. Wet-dry cycles can produce interesting chemistry in experiments, but the amount of exposed land on Hadean Earth is unknown. Meteorites carry organics, but delivery rates, survival, and concentration remain uncertain. Mineral surfaces can catalyze reactions, but moving from assisted chemistry to self-sustaining evolution is a profound step. The origin of life remains open not because there are no mechanisms, but because there are many partial mechanisms whose connection has not been fully demonstrated. The Hadean is the geological stage on which these mechanisms must fit. It constrains them with heat, impacts, atmosphere, water, crust, and time. By the later Hadean, Earth may have offered a restless but chemically rich world-warm oceans or basins, fractured volcanic crust, impact-generated hydrothermal systems, reactive minerals, volcanic gases, delivered organics, and cycles of destruction and renewal. None of these proves that life had begun before the Archean, but together they show that the transition from planet formation to biological possibility is not a clean break. The chemistry of the margins belongs to the same story as core formation: magma oceans, bombardment, and early water. It is what happens when a planet becomes stable enough in places to let complexity accumulate, while still active enough to supply energy and fresh materials. The next threshold is therefore not the sudden appearance of a living world, but the gradual persistence of environments where water, crust, atmosphere, and interior remain connected for longer spans. As the Hadean gives way to the Archean, the question begins to change from whether chemistry can find a foothold at all to whether those footholds can endure. The passage from the Hadean into the Archean is not a clean sunrise over a finished planet. It is a threshold crossed unevenly, through cooling surfaces, lengthening intervals between major impacts, more persistent water, and crust that begins to keep its place for longer than before. The boundary near 4 billion years ago is a human division placed on a natural transition that did not happen everywhere at once. Earth did not leave fire behind in a single moment. Magma still rose. Impact still came. The atmosphere remained without breathable oxygen, and the surface still carried the marks of a young interior. Yet something important changed in the balance of the planet. Destruction no longer seemed to dominate every surface story. The outer Earth had more time to respond, to alter, to bury, and to preserve. The Hadean had been a time when the basic planetary systems were assembled under repeated disturbance. The earliest Archean begins when those systems become more continuous. Not gentle, but more capable of lasting. The decline of the largest impacts matters because it gives time back to the surface. During the earlier Hadean, a basin, crustal patch, or chemical environment could be interrupted before it had much chance to develop. As leftover debris in the inner solar system is swept up or scattered away, the intervals between severe collisions grow longer. This does not make Earth safe by modern standards, but it changes the rhythm. A crustal region can cool more deeply before being remelted. Sediments, if they form, have a better chance of accumulating. Hydrothermal systems can persist around volcanic or impact-heated terrains. Water can remain in basins without being repeatedly returned to steam on a global scale. The atmosphere can evolve through volcanic supply, chemical reactions, and escape to space rather than being reset only by the next enormous impact. In geological terms, persistence is not calm. It is the chance for processes to continue long enough to leave consequences. Crust becomes central to this transition. Earlier crust may have formed often, but much of it was destroyed, recycled, or transformed. Near the Hadean-Archean boundary, larger portions of crust begin to survive in ways that later geology can recognize. The oldest preserved rock terrains on Earth are still rare and heavily changed, yet they show that by the early Archean, the planet could maintain solid surfaces long enough for volcanic sequences, sediments, and altered rocks to be kept within the crust. These ancient terrains are not pristine windows into the beginning. They have been folded, metamorphosed, intruded by later magmas, and weathered across immense time. Still, their existence marks a shift from mineral memory alone toward rock memory. A zircon grain can carry a Hadean signal inside younger sediment, but Archean rocks begin to hold broader arrangements, volcanic layers, chemical sediments, and structures that can be interpreted as parts of ancient environments. The style of early crustal growth remains one of the important uncertainties. Modern plate tectonics may not have operated in its full present form at the start of the Archean. The mantle was hotter, the crust may have been weaker, and the balance between sinking plates, stagnant lids, mantle plumes, and local overturn may have differed from later Earth. Yet the planet was clearly moving heat outward, making new crust, altering that crust with water, and returning some material toward depth. The first stable nuclei of continental crust may have begun to grow from repeated melting, thickening, and chemical differentiation. Continental crust is generally lighter and more silica-rich than oceanic crust, which helps it resist sinking back into the mantle. Once such buoyant material forms, even in small fragments, it can become a seed for later growth. The early Archean does not need broad continents like those of the modern world. It needs only enduring pieces of crust that can survive, be reworked, and gather new material through time. Water also becomes more persistent across the threshold. The Hadean already may have had liquid water in places, as the zircon evidence suggests, but the Archean presents stronger signs of lasting surface water. Sedimentary rocks, pillow lavas formed when lava erupts underwater, and chemical deposits all point toward oceans or large water bodies by early Archean time. These waters were not modern oceans in chemistry. They likely held little or no free oxygen, carried dissolved iron more easily than today, and interacted with volcanic crust and a carbon dioxide-rich atmosphere. Their colour, acidity, temperature, and dissolved minerals may have varied widely. Yet the presence of persistent water changes almost every surface process. It allows erosion, transport, deposition, chemical weathering, and hydrothermal circulation to operate across longer spans. It turns volcanic land and seafloor into reactive surfaces. It gives the atmosphere a partner in climate regulation, because gases can dissolve, minerals can form, and carbon can move between air, water, and rock. The atmosphere at the Hadean transition remains foreign to modern lungs. Oxygen is not yet accumulating as a major gas. Carbon dioxide, nitrogen, water vapour, sulfur compounds, methane in some settings, and other volcanic gases likely shape the early climate. The faint young sun still gives less energy than the modern sun, so greenhouse gases may have been necessary to keep surface water from freezing globally. This is one version of the faint young sun problem. Geological evidence points toward liquid water early in Earth history. While stellar evolution indicates that the young sun was dimmer, the solution may involve higher greenhouse gas concentrations, different cloud behavior, lower planetary reflectivity, or a combination of factors. The important point is that by the Archean threshold, climate has become a planet-wide negotiation among sunlight, atmosphere, ocean, crust, and internal outgassing. Earth is beginning to regulate surface conditions through interacting systems, even if those systems are still immature and unstable. This longer persistence also changes the meaning of chemistry. In the Hadean, useful environments may have appeared in short-lived margins such as vents, basins, fractures, wet-dry surfaces, and impact-heated systems. As the Archean begins, such environments can endure and recur across broader settings. Hydrothermal circulation can run through oceanic crust. Volcanic islands or shallow basins can weather and erode. Minerals can concentrate dissolved compounds. Organic molecules delivered by impacts or formed locally can be altered, destroyed, or incorporated into new reactions. If life had already begun by the earliest Archean, it would have entered a world still harsh, but increasingly able to sustain habitats. If life had not yet begun, the new persistence would have made the search space larger and more stable. The boundary does not answer the origin of life. It changes the stage on which that origin either has happened or is about to happen. The earliest widely discussed signs of life come from ancient Archean rocks, though their interpretation can be difficult and debated depending on the evidence. Carbon isotope patterns, microscopic structures, stromatolite-like formations, and chemical traces have all been examined as possible records of early biology. What matters for the Hadean story is that by the Archean, Earth has become the kind of planet that can begin preserving such arguments. The question of life moves from pure planetary preparation into the rock record, still uncertain but less invisible. Biology, once established, will eventually transform the atmosphere and surface chemistry. But at the start of the Archean it would have been microbial, local, and chemically subtle. The planet does not yet announce life through oxygenated air or large organisms. It allows life, if present, to work quietly in water, sediment, and mineral surfaces. The transition also narrows the role of speculation. Hadean reconstruction depends heavily on indirect evidence, models, meteorites, lunar records, and mineral fragments. Archean reconstruction still requires caution, but it gains more rock, volcanic belts, ancient gneisses, greenstone terrains, and chemical sediments begin to carry information about crustal growth, ocean chemistry, and surface conditions. Gneiss is a metamorphic rock formed under heat and pressure, often showing banded textures created as minerals separate during deformation. Greenstone belts are ancient volcanic and sedimentary sequences altered by metamorphism, and they preserve some of the earliest recognizable pieces of Earth's surface history. These rocks do not restore the first eon, but they show what Earth was becoming as the Hadean ended. By the time Earth is entering the Archean, the planet is still young, but it is no longer only in the act of becoming a planet, it has become an environment. A planet is a body with mass, layers, heat, and orbit. An environment is a place where conditions persist long enough to matter to chemistry, water, minerals, and eventually life. The Hadean built the body through accretion, impact, differentiation, magma oceans, outgassing, crust formation, and the arrival or survival of water. The Archean inherits those systems and gives them longer duration. Oceans become more enduring. Crust becomes more preservable. Atmosphere becomes more connected to surface reactions. Interior heat continues to drive volcanism and circulation, but not every surface is immediately erased. The threshold is not peace, it is continuity. Earth crosses it carrying scars from Theia, heat from its formation, gases from its mantle, water from mixed origins, and crystals that remember conditions older than the rocks that hold them. What lies ahead is the first long chapter of a habitable planet. But the Hadean never fully disappears from that story. It remains beneath it as the hidden preparation, the immense interval in which the world learned to hold a surface long enough for history to begin accumulating. The Hadean remains partly hidden because Earth did not keep its first face. The world that formed from dust, metal, impact debris, and molten rock was also the world that destroyed much of its own beginning. Its earliest crust was recycled or melted. Its first basins were overwritten. Its first atmosphere was altered, lost, and rebuilt. Its first waters left only indirect traces where they touched minerals that later survived by chance. The result is not a simple gap, but a difficult kind of knowledge, one built from fragments that have to be joined carefully without pretending they form a complete picture. Earth's first eon is known through meteorites, lunar rocks, ancient zircons, chemical ratios, impact models, experiments with molten silicate, and comparisons with other rocky worlds. Each source speaks in a different way. None tells the whole story alone. The Hadean is therefore not mysterious because science has no evidence for it. It is mysterious because the evidence is real, powerful, and still too narrow for certainty. One of the largest unknowns is the exact sequence of Earth's cooling. A molten surface almost certainly existed during major stages of accretion and after the Moon forming impact. But the duration and extent of those magma oceans remain uncertain. Did the outer planet remain globally molten for long intervals, or did it cool quickly into a crust that was then repeatedly destroyed by later events? Did different regions recover at different rates, creating a patchwork of crust, lava plains, hot basins, and vapor-covered melt? The answers matter because cooling controls when water can condense, when minerals can preserve chemical signals, and when surface environments can persist long enough to matter. A world that stays molten for a very long time offers fewer opportunities for early water rock chemistry. A world that cools in pulses may create repeated windows of possibility between destructive events. The distinction has to be drawn from thermodynamics, mineral evidence, impact history, and ancient crystals. The origin and survival of water remain equally complex. Earth now holds water at the surface, in minerals, and in the mantle. But how much arrived during accretion? How much came later from water-bearing bodies? And how much was lost during giant impacts are still debated. Some water may have been present from the beginning of Earth's growth. Some may have been delivered after major melting events. Some may have been stored deep enough to survive conditions that erased surface reservoirs. Some may have escaped to space after sunlight split water vapor and hydrogen drifted away. What remains uncertain is the balance among these pathways. That balance changes the story of habitability. Early survival would allow surface water soon after Earth's most violent formation events. Later delivery would place the first enduring oceans in a different stage of recovery. The Hadean record allows both persistence and loss, but it has not yet fixed their proportions. The nature of the first crust is another unresolved part of the story. Ancient zircons imply that some kind of differentiated crust existed early, and oxygen isotope signals suggest interaction with liquid water. Yet a zircon grain is not a continent. It does not reveal how much land existed, how thick the crust was, or whether early crust moved in a way that resembled modern plate tectonics. Earth may have had a stagnant lid broken by volcanism and impact. It may have had episodic overturn, with dense crust sinking in local or regional events. It may have moved toward plate-like behavior earlier than once thought. Each possibility changes the circulation of heat and chemicals. Plate tectonics helps recycle carbon, water, and crustal material on modern Earth. But early Earth may have used different mechanisms to perform some of those exchanges. The oldest direct rocks are younger than the oldest mineral evidence, and the rocks that do survive have been altered by later history. The first crust was essential, yet it remains largely absent from direct view. The timing of the moon-forming impact also leaves important questions. The giant impact hypothesis explains much about the Earth-Moon system, but it does not settle the precise size, composition, angle, speed, or aftermath of the collision. The Moon's isotopic similarity to Earth creates a constraint that any model has to meet, while its small core and volatile depletion point toward a hot silicate-rich origin. The main event is no longer a vague speculation, but its details still matter. They influence how much atmosphere Earth lost, how deeply the mantle melted, how much water survived, how fast the planet spun, and how the early Moon evolved away from Earth. A single event stands near the center of the Hadean, but even that event is reconstructed through consequences rather than direct scars. Bombardment remains another uncertain rhythm. The early solar system clearly contained far more debris than it does now, and Earth was struck repeatedly. What is harder to determine is whether the inner planets experienced a sharp late spike in impacts or a longer, gradually declining storm. The lunar surface preserves clues, but lunar samples come from limited places and have histories of their own. Earth's record is worse because the crust that would have held many impact structures has been recycled or transformed. This uncertainty matters because bombardment affects every other part of the Hadean. It can vaporize water, strip atmosphere, melt crust, deliver volatiles, expose minerals, and create hydrothermal environments. If impacts arrived in a late intense pulse, they may have reset environments that had already begun to stabilize. If they declined more smoothly, then early environments may have had more continuous chances to develop. The origin of life remains the deepest open edge, and the Hadean is central to it without offering a final answer. The Eon may have provided hydrothermal systems, wet-dry basins, mineral surfaces, volcanic gases, impact-delivered organics, and chemical gradients. These are plausible ingredients and settings, not proof. The first living systems required more than organic molecules. They required some way to preserve information, maintain boundaries, use energy, and reproduce patterns with variation. No preserved Hadean fossil records this transition. No ancient rock shows the moment when chemistry became biology. The earliest possible biological evidence comes later and is often debated. This means the Hadean can be described as a stage of preparation rather than a confirmed birthplace. It may have hosted the origin of life. It may have built the conditions that allowed life to emerge just after. The distinction remains unresolved because the evidence thins exactly where the question becomes most important. This incompleteness should not make the Hadean feel empty, it should make it feel carefully bounded. Some things are well supported. Earth formed from material in the young solar system, grew through accretion, differentiated into core and mantle, experienced extreme heating, and gained a moon after a giant impact. Volcanic outgassing and impact delivery helped create early atmospheres. Liquid water may have existed surprisingly early. Ancient zircons preserve evidence from vanished crust. Impacts and internal heat repeatedly remade the surface. Around these supported points lie the open spaces how long each stage lasted, how global each condition was, how early stable crust appeared, how persistent the oceans became, how active the first tectonic style was, and whether prebiotic chemistry crossed the threshold into life before the eon ended. The value of the Hadean is that it teaches a different way of thinking about beginnings. A beginning is often imagined as a clean first scene, but Earth's beginning was not clean. It was cumulative, interrupted, and partly erased. The planet did not move from chaos to order in a single direction. It formed order inside disturbance. Core and mantle separated while impact continued. Crust appeared while the interior remained hot enough to destroy it. Water may have condensed while later strikes could still return it to steam. Atmosphere rose while sunlight and collision stripped portions away. Chemistry gathered in margins while the larger world stayed unstable. The first eon is therefore a history of partial persistence. Nothing had to be permanent at first to become important later. A short-lived crust could alter water. A temporary basin could concentrate molecules. A crystal could outlast the rock that made it. A catastrophic collision could create the moon and reshape the future into something more stable than the past. What remains unknown is not a failure of the story. It is part of the story's structure. The Hadean sits at the boundary between planetary formation and planetary memory. And that boundary is naturally difficult to read. It is close enough to leave traces, but too violent and too distant to leave a full archive. The Earth that later supports oceans, continents, atmosphere, and life begins as a world that repeatedly loses the evidence of its own assembly. Yet enough survives to give the darkness edges. A few minerals, a companion moon, the chemistry of meteorites, the motion of the Earth-Moon system, and the behavior of molten rock all point back toward the first conditions. The picture remains incomplete, but it is not blank. The Hadean closes with Earth still young, still hot, still without the living surface that will later define it. But no longer merely a mass of gathered debris. It has become a layered planet with water somewhere in its system, a sky above it, a moon beside it, and a surface beginning to last long enough for the next eon to keep a record. The first chapter ends as all deep beginnings do, not with certainty, but with a world prepared for history. After the Hadean, Earth no longer belongs only to formation, it belongs to continuity. The surface is still young, the air is still strange, and the oceans, if they have gathered with any endurance, move across a world without forests, animals, or oxygen-rich skies. Yet the deepest transformation has already taken place. Scattered material has become a planet, a molten body has become layered, a sky has risen from stone, water has found ways to remain. The moon keeps its quiet orbit, carrying the memory of a collision that Earth itself can no longer show. Beneath the crust, heat continues to rise, not as a final violence but as a long internal rhythm, feeding volcanoes, moving rock, and returning gases to the surface. Nothing about this world is finished, but it has become capable of keeping time. That is the gentle significance of the first eon. The Hadean does not offer a complete archive. and it does not need to. Its fragments are enough to reveal the shape of a beginning that was never simple. A crystal remembers water, a lunar stone remembers impact, a chemical ratio remembers separation, a missing rock record remembers destruction by its own absence. From these small survivals, the first Earth becomes visible only in outline, but the outline is profound. It shows a planet assembled through disturbance, made habitable not by escaping change, but by passing through change until some conditions could last. The next chapters will carry oceans, crust, chemistry, and life into deeper time. But beneath all of them remains this hidden foundation, the eon of heat and erasure, where Earth first became a world with a future